What's up, everyone? Welcome to the Chem 2325 Exam 1 review. I'm low-key, high-key, very sick right now, and there is a big chance I may die while recording this video, but that is the least of my concerns. My biggest and only concern is you failing your upcoming exam, because that's what's going to happen if you don't watch this video. So I'm glad you're here, because this stuff is very, very difficult, okay? I might be over-exaggerating, but I took this exam a couple years ago and it was very bad. Some of y'all have taken your quizzes already and you've seen how bad it is. Even the smartest of smartest students, who got near perfect scores on all of their quizzes and exams in OChem 1 and are straight A students, they find this stuff difficult. Of course, there's going to be a small minority that thinks I'm full of BS and they find this easy. But for the vast majority, this is difficult. It's very new. It's very different from all the other things you're used to. So, just to give you a little glimpse of how bad this stuff is, take a look at this text message I received the other day after the first quiz. We got people apologizing to me. Like what? Why are people apologizing to me for doing bad on their quiz? Apologize to yourself or apologize to your parents or something or your professor. Why are they apologizing to me? But I can't even blame them because this stuff makes you do weird things that you wouldn't normally do. Me, when I took this exam, what I did was after I was done, I just stepped outside the exam room. I stared at the sky and I asked God, what is my purpose in life? I've never done this ever in my life, but this exam made me do that. So that is proof that this stuff is bad. It's going to change your entire brain chemistry. This is what's going to happen. I don't know if you have seen this meme, but it's very, very relatable. But it's okay because you're here, so we're going to be okay, right, guys? So this is the order of stuff that we're going to cover. I'm going to cover all the different spectroscopy and spectrometry. And within, sections 1 through 4, I'll have examples focusing just on those things. So in the CHEM section, we'll work on stuff that is just related to CHEM, not including anything else. Then in section 5, we'll do some ranking, which is related to the other 4 things. And then in 6 and also 8, we'll start combining things. So you'll have questions that use both CHEM and C-NMR, or maybe IR and mass spec, or some combination of that. And there's also one more part of this, which is number 7, which is your alcohol reactions. That's the only set of reactions you need to know for this exam. And you'll find that a lot of it is pretty much identical to what you covered in OChem 1. And I'll say this right now, I'll mention it again when we get there, but you do not need to remember any of your OChem 1 reactions. If they give you something that was introduced in OChem 1, then you have to know that, right? But they're not going to ask you to remember something and not reintroduce it to you. For example, ozonolysis, this will never show up again, and they're not going to ask you to do it because it doesn't show up again, right? Even though this was something from OChem 1. However, something like tosyl chloride or tosylation, this was an OChem 1 thing, but they do reintroduce it here, so you do have to know it, right? So don't worry about all the other things, especially alkyne reactions and a lot of these alkene reactions. If you need to know something, they'll tell you. If not, then they won't tell you. Another thing is the concept of a nucleophile, something with a negative charge being able to attack something with a positive charge. That concept remains throughout OChem. So obviously don't forget that because this is a foundational thing. It's not something that you should need to remember. It should be something that you just know at this point. But yeah, and then some of your SN2 stuff, SN2 in general is not going to show up, but there are SN2 type reactions. And once again, you'll see them, right? They'll show them to you if you need to know them. So that's all I'm going to say about that. And I'll probably mention this again when we get there. So let's start with infrared or IR spec. I want to mention one more thing. So when I took this exam, the whole time I thought that the hard part was having to memorize all your values for IR, NMR, etc. And then I went there to the exam room on the exam day and they gave us the sheets. And I knew I was cooked because if the hard part in my mind was memorizing all these values and they're giving it to me, holy shoot, man, like that means there's something worse ahead, right? I mean, the hard part is putting all the pieces together. It's like, it seems easy, right? They give you all the values, all you gotta do is put together. But I'm not gonna tell you it's easy. Like, obviously for me it's easy, but this stuff, like when I was taking OChem 2, the first exam, I didn't understand it. And even as time progressed and I got to the finals, I was mainly just worried about this stuff, even though I knew it was going to be a very small portion of the final exam, probably like literally one question it ended up being. I was worried about this because it was difficult. Like, I understood what was going on, but I just couldn't put things together. But then, you know, when I actually had to start teaching this as a TL leader, this happened like, 8 months between my finals and having to lead, right? 8 months of time had passed and I had to start teaching this. I automatically knew how to do everything and I just had so much skill. And people might think, yeah, you had 8 months to like learn all this stuff, so that makes sense. No, literally, like, between the time that I took the final and me starting teaching this, I didn't do anything. In fact, I was not even planning to teach OChem 2. I was planning to go back to Gen Chem after teaching OChem 1 in the fall because I had no desire of doing any of this OChem 2 stuff. But I was kind of forced into it and magically I just knew everything. So what does that tell you? This stuff it's a skill, right? It takes time. You might not get to the point where you're like a master at it right now, and that's fine. Just do as good as you can. This test might end up being easier than you and I think, but let's say you do fail this exam or you don't do as good as you want and you want to drop it. You can drop it, right? Don't forget that your exam 2, you can use that to carry your grade, and then your final can replace everything. Objectively, exam 2 and the finals are like harder than OChem 1 stuff just because there's a lot of new reactions, but that's all it is, right? It's just reactions, and you guys know how to deal with reactions now, so you'll be good with those, right? It's no more of this new random stuff. It's just pure reactions and putting them all together. So if you haven't understood a single thing I said, all I'm saying is that it's okay if you do bad on this exam. Like, don't worry too much. Don't let it define you. Like, it's not the end of the world because a lot of people did horrible or even failed this exam and still ended up with A's thanks to the curve and whatever syllabus rules we have. So that's all I'm gonna say, right? But still, if you can do good on this exam, that's always the best case scenario. So let's start. Okay. So with IR, right, we have these values. I'm sorry that this thing is cut off, but like this is the least likely functional group you're going to see, the amine. So I'm not going to tell you what's supposed to be there. But anyways, we have all these values. So that's obvious, right? Like there's no point in me telling you the values again, but you need to understand like how different values show up in different scenarios. And I just want to point out different things, right? The first is we see that we have an alcohol at 3,300, but then it shows an alcohol again at 3,000, and they both say they're very broad. So like, what does that mean? Obviously, the top alcohol is referring to just an alcohol, so something like this, whereas the bottom one says acid, right? So meaning it's part of a carboxylic acid or connected to a carbonyl. So what is the difference? If you look at an IR, let's put 3,000 right here, 2,500 here, and then 3,500 here. Okay, if you're looking at just a regular alcohol, your peak will be above 3,000, right? So it's gonna look something like this. It's broad, and look at the boundaries, right? It never goes below 3,000. And it's centered around 3,300. That's why it says 3,300 over here, because it's generally centered around that. This might be even shifted more to the left. Doesn't matter, right? The point I'm trying to make is that it's never going to go below 3,000. However, with your carboxylic acids, let's do the exact same thing. We're going to make this, and let's put 3,000 right here, 2,500 here, and then 3,500 here. This one is going to be centered around 3,000, and it's going to look very like funky like that, okay? Look, I know it kind of comes to like a point here. Sometimes it's even more narrow like that. Sometimes it'll look like that, right? But if you look at the peak as a whole, look at the boundaries. The boundary goes from here to here. this thing as a whole is very broad. So that is indicative of a COOH, or a carboxylic acid. Now, another thing to note is look how messy it is, right? This is very messy, and there's a big chance that you have other peaks overlapping here, which is why sometimes you can get narrow stuff like this, or stuff like this, right? So the fact that you have something like this, like, it should tell you that there is a carboxylic acid specifically and not a regular alcohol present. So, oh, sorry, by the way, I'm probably going to be drinking a lot of water throughout this video. So if I take random pauses, that's what I'm doing, because I'm like dehydrated and I can't even breathe properly because once again, I'm sick. So yeah, just forgive me for real. Anyways, that's what I want to point out about, OHs, okay? But in both cases, they're broad. Just remember that the alcohol will be above 3,000, whereas the COOH, carboxylic acids, will go all the way down to 2,500 and will look messy, whereas this will look pretty neat. Okay, what about amines? Amines are NH, right? So we have three types of amines. We have primary amines, which means you're connected to one carbon. We have secondary amines, which means you're connected to two carbons. And we have tertiary amines, which means you're connected to three carbons and therefore 0 hydrogens. So on your on your IR, okay, you're going to have here, I'm just going to point this out already before I mention it. So all of your peaks that have H's are going to be 3,000 and above. Take a look at this chart. You'll notice that all of the stuff 3,000 and above have H's involved. The only one that's going to be a little bit below 3,000 will be your alkane, right? It's just below 3,000, but they're very high, okay? So I want you to just remember that. It makes your life easier. People ask, even though we're given the charts, should we just memorize them? Because that's what my professor said. In my opinion, you don't have to memorize anything, okay? You just memorize. If you do this stuff a lot, you'll get used to where certain things are located, and knowing these little patterns will make it easier in locating them on your chart in the case that you don't memorize everything. So if I find little patterns like this, I'll point them out, right? Like I just mentioned right now, the hydrogen peaks will be very high. So if you're looking for an H peak, then look at the 3,000 plus range and you'll find it. If you're looking for triple bonds, look at the 2,200 range, etc. Okay? So anyways, we have our amines. Now, your amines, let's talk about primary first. In general, the NH bonds are going to show up as narrow like that, narrow and sharp. So for NH2, it's going to look like this. And for NH, it's going to look like this. Now, obviously, this is supposed to be over here. I just put it on the right side so you can see both of them. But what is the difference? In one case, we have two little peaks over here, and the other one we have one. Which one corresponds to which? This one, the left one, corresponds to primary, and the right one corresponds to secondary. Now, people get this mixed up. They're like, oh my god, primary but 2, and then secondary but 1. I keep mixing those up because they're flipped. That's not how I think about it, okay? I don't even like to classify primary and secondary. All I go with is how many NH bonds are there. In a primary, what does this actually look like? You have 2 NH bonds. Therefore, you're going to have 2 peaks resembling that. That's why this is coming from a primary, which has 2 NH bonds, okay? This one, on the other hand, the right one, is bonded to 2 R groups, so only has 1 NH bond. Therefore, there's only 1 peak. But don't forget, they're going to be above 3,000, right? Generally, as it tells you, 3,300. Obviously, some deviations might occur, but above 3,000, a sharp peak like that will most likely mean that you have an amine. Now, what does this tertiary amine? This tertiary amine has nothing, right? Has nothing in terms of NH. So you might have an amine present in your molecule, but if it's not a primary or a secondary, then you just won't have anything in the 3,000 to the 4,000 range, right? It would just look like this, unless you have something else that's in that range, right? So that's that. Okay, moving on. Let's talk about alkanes and alkenes. So it says right here that the CH bonds are just below and just above 3000. Let's talk about that, right? And let's also include alkynes. So let's put 3000 right here, and then 4000 right here, and then 3500, okay? So when it comes to alkanes, right? So just something like this, the H's that are on these sp3 carbons are going to show up as peaks right above, right in front 3000, right? So they might even be sharper like that, right? But they're not going to like really cross this. I'm so bad at this. Just pretend it's not crossing the 3000. It's not going to cross the 3000 line, right? But the moment it crosses it, let's say you have like this right here. That, let's say this is like 3050, okay? That must most likely mean that you have sp2. So this means an alkene. So something like this, right? This bond right here, the sp2 carbon's hydrogen, that's going to be just above 3000. Now, what if you have a terminal alkyne? That's an sp carbon, and we're looking at its hydrogen. That is going to be, I'm so bad at drawing these. Let's say this right here is 3300. You're going to have a peak right here at 3,300. It's going to be pretty sharp. Okay, so now it comes the issue, like if I have a peak over here, is it going to be an amine that's secondary, or is it going to be a terminal alkyne? Use other clues, okay? Sometimes the amine will be like shorter, so that might be a giveaway, but don't just depend on one thing, right? They'll give you multiple things to confirm your answer. So that's what I want to mention with regards to this. So one more time, just to re-emphasize, your sp3 will be just above 3000, and they'll be pretty good. Like they're not going to be short like this. They'll be like pretty strong. sp2 will be just above it, and then sp will exceed it by a lot and go all the way to 3300-ish, okay? So that's how you can know the different types of hybridized carbons that you have present. Okay, now what else, right? We talked about some of these peaks, like we talked about carboxylic acids and we just talked about alkynes. But as I mentioned, there's more than just one type of peak. All we talked about so far was peaks involving hydrogen. But if you look at this 2200 area, right, we have peaks resembling C triple bond C. So if you had an alkyne like this, what would you expect to see? You would expect to see a peak obviously at 3300 because we have a hydrogen here, okay? Don't forget, this only happens if it's terminal, so you have to have a hydrogen present. Then you're gonna have like a peak right here, right? 3300. But you're also going to get a peak at around 2200 to 2100, right? So you'll have, whatever going on, and then you have something over here, okay? And actually it's gonna be pretty short like that, but you'll have like a noticeable peak at 2200. That is likely a confirmation that you have in alkyne, and specifically a terminal alkyne, because we have both the C triple bond C peak and we have the sp carbon H peak, okay? So that's what I mean by you can confirm if you have something with other clues, okay? I'm not gonna talk about literally everything, so I'm gonna skip nitrile just because, you can just read that. I don't have anything to add to that one. But let's talk about carbonyls now. This is a very like long list. Like there's a lot of stuff in this list, okay? So first of all, in general, C double bond O, we refer to this in the IR world as carbonyls, okay? Even though a carbonyl functional group only refers to ketones in aldehydes, when we're talking about IR, NMR, all that stuff, we're going to refer to anything that's C double bond O as a carbonyl, because if you have something like a carboxylic acid or an ester, okay, it's not that an entire functional group shows up as one specific peak. Different parts of a functional group will show up as different peaks, and you put them together to find the overall functional group, okay? So when we look at something like this, this is not a carbonyl, it's a carboxylic acid derivative, but for the sake of IR, we're going to refer to this as a carbonyl because this will have a C double bond O peak, and this will have another thing, and so on, okay? So I want to make that clear. Now, obviously, as we can see, the C double bond O has its own peak. So before I even get into it, for carboxylic acids, we already talked about this thing being broad from 3,500 to 2,500. But another way you can prove that you potentially have a carboxylic acid is by the peak that's represented by the C double bond O, which we're going to talk about. So carbonyls in general are going to be about 1640 to like 1780 maximum. And this involves everything, okay? This involves, as you can see over here, ketones, aldehyde, esters, carboxylic acids, amides, acid chlorides, and whatever else there is. So we can't just say, okay, every single one of our carbonyls will fit in this range. That is not the case. Within this range, different functional groups will be at different parts of it. Okay, there's going to be some things that are at the bottom end of it. There are some things that are going to be towards the upper end. If something's at the higher end, it's not going to be ever found at the lower end, and vice versa. So you definitely want to know, what do we normally see where within this seemingly small range, okay? Because it's very important. So the highest, let me low-key flip this just because on a chart we go right to left in increasing order. So the largest stretch will come from your acid chlorides, which is not on this list, but you still need to know it. Okay, so this will be pretty high, like let's go 1750 to 1780. Next will be your esters. Esters will be like 1740 to 1760-ish. And then come your ketones, aldehydes, and carboxylic acids. These are all like very similar, like, I don't know, 17 to like 1730-ish. Technically, ketones are a little bit less than aldehydes, but the good thing about these three is that you can like prove which specific one you have. And I will get into that in a second. So I don't really care about which one's higher than the other because they all are very similar anyways. Now, next we're going to have our amides, which will be like 1640 to 1680. And once again, this is another instance where you can prove that you have an amide other than the carbonyl stretch. So I'll really quickly tell you why the ranking is like this, but it doesn't really matter. The first thing is that, first of all, like amides, okay, something you should know is that whenever you have resonance involved with a atom that's involved in a certain stretch, then that is going to decrease your frequency. And the rule of thumb is like 20 to 40 per conjugation. So when you look at your amide, there is resonance, right, with the carbon, and carbon is part of the carbonyl stretch. So there's resonance with the thing involved with the carbonyl stretch, making the value decrease from what you normally expect other carbonyl stretches to be in. But this ends up being decreased more than 20 to 40. Another reason for this is just inductive effects. Nitrogen is not as electronegative as something like oxygen, and it has like electron donating type effects, causing it to be very stable. And when something is pretty stable in the IR world, it tends to be a lower frequency, okay? So that's why amides are going to be your lowest. Now you might be wondering, okay, what about oxygen? Oxygen can resonate. Why would this be very high and not very low? This one, there's a couple of reasons. First of all, like we know that any OR or OH group is an electron donating group, but in this specific instance, the electronegativity of oxygen overpowers its electron donating effects. And this resonance that you see is actually not as likely as you think. It's not as stable as you would expect because this involves oxygen donating its electrons, and oxygen is very electronegative. It's the second most electronegative element, and it wants to keep its electrons. So in this specific instance, it's having a kind of like an opposite effect, which is, you can think of it as like a less stabilizing effect, which is making it at the higher range of our overall carbonyl stretch. And for that exact same reason, acid chlorides end up being the highest. Now, you're also probably wondering, okay, isn't oxygen more electronegative than chlorine? Why is chlorine molecule higher? Because there is still technically some resonance here. So the fact that there is some resonance means that it mitigates the electronegative effects of it. I'm just spewing some BS, but I promise you, It's not BS, okay? It sounds like it, but it's not. But anyways, right? Chlorine also has lone pairs. You might think, why does this not resonate? Something to do with orbitals. I'm not going to go into it, but just keep in mind acid chlorides are your highest, and then esters are a close second, and then this is the order afterwards, okay? Just ignore me. But I do want to re-emphasize that resonance can decrease frequencies. And this is important when it comes to ranking. Okay, they're never going to ask you what is the exact freaking value of this. And if you put 1700 instead of 1701, they're going to give you 50 points off. That's not going to happen. Okay, they don't ever ask you this. They're either going to give you a ranking question and they're going to be like, compare this to this, or they'll just give you a chart with representing a molecule, and then you got to kind of piece it together. So one more time, resonance is going to decrease your frequency by about 20 to 40. And so if you were ranking these and they were asking which one has a higher C double bond O stretch on the IR, this one would be the higher one and this would be the lower one, just because this one has resonance with this sp2 carbon, whereas this one doesn't have anything. So that's what I want you to get out of this. Okay, back to this stuff right here. How do we, confirm these other things? So acid chlorides, the fact that they're that high, I think that's already proof. Like, you don't really need extra proof to know that you have an acid chloride. So I'm not really gonna say anything about this one. If you have something at 1780, that's definitely gotta be something like an acid chloride. Same with esters. Like this one, you can't really prove it other than the carbonyl stretch, just because. What else do we have? We have C single bond O. This is not really like gonna help you because I didn't mention this, but there's something called the fingerprint region, which I think everyone is aware of. The fingerprint region is going to be about 1500 and below. 1500 and below is going to look like this. It's not gonna make sense, okay? There might be things, like there might be a CO stretch at here at 1200 or something, but you can't really actually decipher what you're looking at, and it's always going to look like a chaotic mess. So you never look at the fingerprint region, and since C single bond O falls in the fingerprint region, there is nothing else to show that you have an ester. So like for the 15 billionth and first time, this is an instance where you can look at other clues. One, you can just see that I have a very high a shift, right? You can also look at the molecular formula. You can also look at the C-NMR or H-NMR they give you, all of those things. So don't worry, okay? There will be other ways to prove it. But with these right here, okay, aldehyde, carboxylic acid, and amides, you can actually prove within the IR that you have this specific functional group. The first one is carboxylic acid. We already talked about this, okay? First of all, you'll have, let's do 2000 right here, and then 1500, and then 3500. No, I'll put 4000 right here, and then 3000 right here. Okay, no. Oh my god, I'm cooked. Hold up. Let's put 3000 right here. Okay, so first you're gonna have a stretch at 17. Let's put 1710. Next, you're also gonna see this thing right here. You're gonna see that, right, where it's going all the way to 2500 and 3500. It's very broad, it's messy, it's obnoxious, but you have this plus the carbonyl stretch. That most likely means you have a carboxylic acid, okay? Next, what if we are looking at an amide? If we're looking at an amide, you're gonna see a carbonyl stretch lower, so around 1680-ish, give or take some. So that's gonna be one thing. You're also going to see this right here, okay? This one happens to be an NH2. It could be an NH. If it's an NH2 or an NH, just look at how many peaks there are. For an NH2, you would expect, like a couple peaks right here at 3,300 to 3,500-ish. If it's an NH, so if you had something like this, then you would expect just one peak instead of the two peaks, right? Now, the only issue is if you have this BS, then obviously you can't prove that you have an amide with the IR itself. You could prove that you have a tertiary amide, but you can't really fully confirm that you have it. So once again, other clues will help you with this. So there's that for amide. Now finally, let's talk about ketones and aldehydes. So ketone doesn't really have anything, but the aldehyde does have something, and if you are missing the thing that the aldehyde has, you most likely have a ketone. So let's talk about it. Okay, first of all, carbonyl stretch 1700. Let's just do 1700 this time. Now, aldehydes, they have this H. They have an sp2 hydrogen, but it's not like a regular sp2 hydrogen. It's coming from a carbon that's a carbonyl carbon, okay? So what is this going to look like? This is going to have what we call our aldehyde fangs. Okay, this is very specific to aldehydes. This right here is 3000, okay? You're going to have these little fangs that come down like this, and they never pass 3000. It's supposed to be like 2750 to like 2950-ish, but they're going to look like this. They're very short, and they come down like that, and they don't pass 3000. If you have a carbonyl stretch plus something like this, that probably means you have an aldehyde. Let's say you don't have this at all and you just have this, you might have a ketone, okay? You definitely don't have an aldehyde if you don't have the fangs. So that's what I want to point out about these. These are things that they don't tell you in class, but I really wouldn't know because I never went to class, but I'm assuming they don't tell you because nobody ever knows these things when I ask them. So I hope you keep that in your mind. Lastly, let's talk about our alkenes. Well, lastly, in terms of stretches, I have more things to talk about with IR. So for alkenes, it says that you're going to get a stretch of 1660, right? So yeah, if you had this, you get a peak at 1660. However, when it comes to benzenes, a benzene is 3 alkenes that are conjugated and they're aromatic, right? So these end up being at 1600. Now, how does this happen? Because look, 1660, and what is the conjugation? There's 3 degrees of conjugation here. So remember what I said, every degree of conjugation, of resonance conjugation is going to decrease your shift by about 20. So if we subtract 3 times 20, since there's 3 of them, you're going to get 1660 minus 60, which is 1600. So that is why that happens. Definitely do not ignore this, okay? The peak will actually be pretty short. So 2000 and then 1500, you're going to have whatever, right? Stuff going on. And then you'll have like a peak like this and then, fingerprint region. So I don't know how this happened. But anyways, do you see this right here? Although it looks very small, we do see a pretty significant yet small peak right here, and it's very low, about 1600. Don't ignore something like this, okay? This cannot be a carbonyl because carbonyl stretches are known for being pretty long like that. Also, this is way too low to be a carbonyl. Carbonyls at the very minimum should be 1640. This is at 1600 flat, and it's very short like this. So that is a likely giveaway that you have an aromatic benzene ring specifically. Okay, what else do we want to talk about? So we talked about how different peaks will appear. I guess let's do a quick terminology review. If you're going to the right, this is called upfield. And if you're going to the left, this is called downfield. And this is important to know because you might get a ranking question that's like, rank the values by their downfield shift. The furthest downfield is rank 1, the least downfield is rank 5. If you don't know what downfield is, you could flip the entire ranking, and you definitely don't want to do that. So make sure you know this. Another thing, let's say they're asking you to rank something like this. They're wanting you to rank the carbonyl stretch of these 2 molecules. Well, both of these are ketones, and both of these are part of a cycloalkane ring. So what is the difference? Obviously, I mean, you might notice something's off about this because it came up in OChem 1 a few times. Don't forget that if you have a 4-membered or a 3-membered ring, these are very unstable due to something called ring strain. Their bond angles are very, very discombobulated, and so they don't like this position. They want to get out of it. So what does this mean? Okay, I want you to put everything together. Ring strain equals unstable. What does that do to your value? What did I tell you about this? I said amides are better than something like better in the sense that they're more stable than something like a ketone because of resonance. What did that do to your value? For amides, this ended up being very low. For a ketone, it ended up being higher. So that must mean stability is correlated to a lower shift. Okay, so what do you think happens here? You're incorrect. It's going to be the opposite of what you just thought. This one will be lower. So this one will be about 1710, and this one will be higher, like 1730 or 1740 or something like that, because this is unstable compared to your cyclohexanone. So that's another factor to keep in mind. Now, that's as simple as you're going to go, right? If you're wondering, like, what if they gave me this and then in aldehyde, what do I do? All these values are very close. They're not going to expect you to know the difference, okay? I couldn't even tell you exactly. Or, maybe they give you like an ester or something. I don't know. They're not going to, no, not an ester. Let's just do an aldehyde. They're not going to make it confusing and expect you to know the very minimal differences. If they give you something like a ring strain question, they're only going to make you have to compare that to something like this. Okay, so within a ranking question like this, they'll probably give you a molecule with an amide. They'll probably give you something with an acid chloride. And then maybe they'll give you another acid chloride with like a fluorine or something, right? So you're only having to compare the ring strain to the normal version of that molecule. You don't have to worry about how much does this deviate. All you have to know is that the deviation that comes from a ring strain will make it more of a shift than the normal version. Does that make sense? I hope it does. Okay. So that is that. What else? Another thing I want to talk about is like there's a ranking question where they'll be like rank by multiple bond stretch in an IR. And, they'll give you some molecules, one that looks like this, one that looks like this, like that or something. I want you to be familiar with this terminology because if they ask you this question and you don't know what they mean by multiple bond stretch, you're going to be like, oh no. And then you're going to send me a text message saying, I'm so sorry, I failed you. I'll do better next time. And you don't want that to happen because I'm telling you what you're going to see on your exam. So multiple bond stretch is exactly what it sounds like. Multiple bonds. Okay, a stretch that comes from a multiple bond. So a C single bond O is a single bond. But if you had a double bond, this is a multiple bond stretch. If you had C triple bond C or C double bond C, this is a multiple bond stretch. What it is not is this, C triple bond C H, okay? This thing you are not looking at because even though you might be tempted because this is such a high value, 3300, this is coming from a C single bond H. If you were looking at a molecule like this, you would be looking at this for the ranking comparisons, okay? Which is at 2200-ish. So make sure you know this, right? So for each of these molecules, you would be comparing the carbonyl stretch to the alkene stretch, not the hydrogen, just the C double bond C, to this one, to that one, right? Now, why am I bringing this up? Obviously to let you know what they mean by that, but there's a very specific thing that tends to show up a lot is something like this. If you get a molecule that is a symmetrical alkyne and it's just pure hydrocarbons, meaning it's fully nonpolar, this peak ends up not showing up at all. You would expect it to be 2200, but it ends up being 0, like nothing. Now, why is this? There is a full cancellation of dipole moments. Now, I know what you're thinking. This is a hydrocarbon. It's nonpolar. Doesn't matter, bro. Like, there still are local dipoles within the molecule. There's absolutely no dipoles anymore just because of the symmetry canceling everything out. And if there's no dipole moments, then that means no matter how much you vibrate this molecule, this bond will not stretch enough to even cause like a peak that you normally see on your IR. Therefore, the C triple bond C will not show up. Now, this molecule will still have IR peaks, right? You'll still have C single bond C, which is going to be in the fingerprint region. And then you also have the bonds to hydrogen, right? The sp3 CH bonds, which are right below 3000, you'll still have those. But for the sake of ranking, something like this would be rank 5, okay? Even if I'm comparing it to like a ketone and like a benzene, 2200 is higher than 1700 and 1600, so you'd be tempted to rank this as 1, but it ends up being the worst, rank 5, okay, or rank 3 or whatever, because there is nothing. I also believe if you have a trans alkene that's also fully symmetrical and is just hydrocarbons, the same thing will occur. But most of the time, they just give you like a symmetrical internal alkyne. So please ensure that you know this, because nobody else will tell you. All right. I think that is it for IR. I don't know how long we spent on this, but let's move on. Oh, great. I forgot about this. So now we're going to put our knowledge to use. We're going to figure out these molecules. So this is a very common type of question. You may have received it on your quiz. I don't know, but they love to throw this at you on your exam. If you don't know what the hell you're looking at, they give you a bunch of molecules and they give you some IR charts, and you just had to match up the molecules to the charts. So what you do is look for different functional groups and see if they match up, right? So over here, okay, I see, let's use this. I see this. This is not going to be your aldehyde fang, okay? Please don't think that. First of all, you don't even have a carbonyl stretch, and aldehyde fangs are like up here, like that. So this just looks like regular sp3ch, so that tells us literally nothing. What else can we look at? I'm gonna let you point it out. This right here, okay? What could that possibly be? It could be, you know, either an amine, or it could be like a terminal alkyne. So we're just gonna keep it. We're gonna keep it in the background, right? We're not entirely sure yet. So we're gonna look at our molecules too. So basically, I see that our molecules, we have J and we also have E, right? These are the only ones that could fit this, because E has a NH and it's just one NH, right? It's not an NH2. So that could be this peak. J has this, where you have a hydrogen, which shows up in that 3300 region. Now, I already know actually like the difference. I already know that this peak is not an SP peak, because SP tends to be like lower, but I didn't mention that on purpose, and just forget I mentioned that because I want you to use other clues here, because you might forget. You might be like, I really don't know which one this is. So how else can we figure this out? Okay, let's take a look. Oh, by the way, it's also not in amide because we don't have the carbonyl stretch, right? So what are we gonna do here? If we had molecule J, we expect two things. We expect a C triple bond C peak, which is supposed to be at 2200. Do we see that? We see nothing, right? 2200 would be over here. We see nothing. We also expect to see this, a benzene, which is going to be at 1600. Do we see that? We don't see anything right here. Therefore, it can't be molecule J. Molecule E has nothing. It just has sp3 carbons with their hydrogens, and we have an amine. And that's all I see on this IR chart. I see sp3 carbons, and I see this peak, which, once again, I wasn't sure if it was an amine, like a secondary amine, or if it was an alkyne. But because of my other clues and the lack of other molecules that fit this, I know that this has to be molecule E. So we're going to go with that. Okay, next one. What do I see over here? I see this. Once again, this is not an aldehyde fang, okay? Aldehyde fangs will look like that. This just looks like that, right? So what is this? This probably means that it's, you know, gonna be like an sp3ch. Usually your sp3chs will be like low like this, but I mean sometimes they won't be, right? It just depends. What else? We see this. I always look for these carbonyl stretches. So this is a carbonyl stretch, and it looks like it's above the midway point, or like, I mean, I drew this, so it's probably definitely not to scale, but I tried to make it obvious that it's around 1700 and not the 1600. So we'll put like 1740 here. Okay, something like that. I also see this. Okay, let me erase, or let me just mark it, right? If you align this, it's above 1500, so it's definitely not the fingerprint region. And it happens to be around 1600. So I have a benzene present. Okay, now I don't know what type of carbonyl I have. I know I don't have an aldehyde, but it could technically be a ketone. So I'm going to see what I have, right? It could be a ketone or an ester. Remember I said esters and ketones, technically you can't really like prove which one you have by the C double bond O stretch itself. So what do we see? I see molecule C has a benzene, and so does A, right? Both A and C have a benzene with a carbonyl. Now, obviously, it can't be A because we're missing that super broad acid stretch, so it's not going to be A. C has some CH3s right here, so that kind of matches this thing right here, and obviously has the benzene and has a carbonyl, which is 1700 and above. So that all adds up, telling me that our answer is going to be C. Okay, the next one is going to be, this third molecule, right? So I see we have this right here, which is, once again, around the midway point, so like 1720 or something. Now this time, I got some stuff, okay? Do you see this? This is the aldehyde things I'm talking about. Now, this entire thing doesn't have to be the aldehyde thing. The aldehyde thing is usually like this thing right here. This right here looks like it could just be an sp3ch. Doesn't really make a difference, but I'm just telling you, like the aldehyde thing I'm referring to is like this. It's pretty high up. Okay, so we see that, and I see 1720-ish. So I probably have an aldehyde. Let me look at my molecules. I see that F looks like it has an aldehyde. Do I see anything else with an aldehyde? I don't see anything else with an aldehyde, therefore this probably is going to be my answer. So I'm going to put F right here. If you're wondering what this is, gang, I have no clue. I think I just drew that in on accident. It's definitely not, like, it's higher than, see, like, you might be thinking, oh, is this like an alkyne? Nah, that's way too high for an alkyne. It's just like a continuation of this thing. So don't worry about that. Okay, last one. What do we got here? So basically, I'm like not looking at any of this stuff, right? The only thing I see is like this, which looks like sp3 CHs. And I feel like I'm cooked. Like, do I see anything else? I don't see anything else, but I'm looking at my molecules to make sure I didn't do anything wrong. Like, if there's no molecule that has just carbons and things that don't have peaks, then like I probably did something wrong. So I'm looking at all my molecules, and it looks like molecule G low-key fits this. Like, yes, there's a bromine, but there's no peak called C bromine. The bromine, all it will do is just like affect the value of your C to C peaks or your sp3ch peaks, but it's not its own peak, right? So a low-key matches up. Therefore, my answer is G. I hope that made sense. But basically, like, because there's like nothing here, it means that there had to have been nothing in the molecule, right? Other than just sp3 carbons. And this happens to be in a ring structure, but it doesn't matter, right? It's just sp3 carbons. There's nothing really to it. Okay. So that is it for IR. Let's move on to NMR. HNMR specifically. HNMR or proton NMR has some things that are different from carbon NMR. The first thing is integration. So integration refers to basically like number of hydrogens that correspond to like single peak. So if you have a molecule like this carbon right here has how many H's? It has 2. And they're both identical, right? It's an sp3 carbon. These can free rotate, so it's identical. They're both identical. So if we were looking at the peak that corresponds to these H's, because once again, it's HNMR, the peak would look like this. It would have a 2H on top. Okay, forget splitting. We're just looking at integration. Integration is this thing. It tells you how many hydrogens are integrated into a single peak. There's 2 of them. Now, what about these right here? There's 3 over here. Okay, so your peak would be 6. What the hell? How did that happen? Because these 3 are also identical. There's a plane of symmetry. So you can look at both sides, right? These 3 are the exact same as those 3. So all 6 of those would be under the exact same peak, making your integration for that 6. Now, if you had like an alkene like this, technically these are different hydrogens, so they should have their own peak. So this should have a peak of 1H, and this one should have a peak of 1H. There might be a professor that says that they are so close to each other in terms of their peak that they just become one single peak. Depends on the resolution, right? Obviously, if you have very small resolution, like, 4 and then 3.9, 3.8, whatever, 3.5, you can like see the location of different peaks. But if your resolution is small, like that, where there's not much space in between, sometimes people will say, okay, they're so close together that they just show up as one peak and they get integrated together. I just want you to keep in mind that these are different hydrogens just because sp2 cannot rotate. But you can confirm with the professor if they would show up as different peaks or if they would be like together. They should be different. That just makes more sense. But once again, everyone has their own opinion on how they want to do these things. So just be mindful of that, I guess, unfortunately. So that is integration. We'll do like one more. Okay, let's look at this one right here. This has an integration of 1H. What about this one? So this molecule is symmetrical, therefore all of these blue are the exact same. So they each have 2 H's, so just multiply it by 3 since there's 3 of them. So that would be a peak of 6H. So that's how integration works, just number of hydrogens under a given peak. Now, what about, so we're done with integration. Now we're going to talk about splitting or multiplicity. We'll use this the same example. This has 3 hydrogens, and then obviously the other one has 3 hydrogens, right? So if we drew the peak of this, it would be integrated by 6. But now splitting, right? We have different types of peaks. We have singlets, we have doublets, we have triplets, and so on, right? We got quartets, then we got quintets, and it just keeps going. Usually 6 and above they call a multiplet. So if you see the word multiplet, it means 6 and more, but they can easily just say how much there are. Like I've seen them on exams say, okay, this peak is a heptet or a nonet. So it's still good to be familiar with these terms, but that's what they're going to look like. Right now, how does this work? There's something called the n+1 rule. So n is the number of adjacent H's. Now, the way I think about this, let me give you an example first. Like, look at this, right? If we're looking at this carbon's hydrogens, we got the peak that's integrated at 6H, okay? But if we want to do the n+1 rule, what do we mean by adjacent? Adjacent, I think of it as the adjacent carbon's hydrogen. Let me write that out. Adjacent carbon's hydrogens. So the H's are on this carbon. I'm looking at the adjacent carbon and seeing how many H's are on that one. So there's 2 over here, okay? There's some thing that the professors taught you about, like 3 bonds away, 2 bonds away, whatever. That stuff is confusing. So I look at, we're looking at the peak of this, okay? Look at the carbon that this peak is on. It's on this one. Now move 1 carbon away. So we're going over here and look at the H's on that. There's 2 of them. So our n value is 2. So if we're doing the n+1 rule, it's 2 + 1 = 3. 3 means it's a triplet. So this peak would be a 6H triplet. Okay, what if we had an ethane like this? These are identical, right? Because this is a symmetrical molecule. So these carbons and H's are identical. So you'd have one peak at 6H. Okay, now what about the N+1 rule? You might think, like, let me just go one carbon over. There's 3 H's, 3 plus 1 is 4. That is not the case here because identical H's cannot split each other. Why do you think we don't say that this splits that or that splits that? Because they're identical. They are next to each other, so technically they should have an effect, but they don't just because they're identical. So even though this carbon and its H's are adjacent to this one, those are identical, so they're not going to split each other. Therefore, this would just be a 6H singlet. Let's do another one. Let's do like a benzene. And we'll do like that. Let's look at this. This has 3 hydrogens. What would the integration be? It would be 3H. And what is he splitting? Okay, we're next to just this carbon and it has 0 H's. So 0 plus 1 is 1. It's a singlet, right? So it's going to be a singlet. What about this? This one. How many hydrogens? It has 1 H. Okay. Now, what is it next to? It's next to this one. And how many H's does it have? It has 1. It's next to this one, which has 3 H's. It's next to this one, which also has 3 H's. So we're going to add all of these up. Okay, we have 3 plus 3 plus 1. That's 7. So N plus 1 equals 7 plus 1, which is 8. That means that we're going to have an octet. So something, right? Whatever. It's going to be called an octet. Now, what if you're on a double bond? We're gonna go with my ruling, which is that these will have different peaks. That's how it should be. But once again, confirmed with the professor. It doesn't matter if whatever I'm saying does not apply. You can just ignore this part, but focus on the other things. But let's say that this is going to be a peak and it's a 1H. What is its splitting going to be? Okay, this time, even though this is on the same carbon as that, and we normally don't split on the same carbon, we can split it because these are not identical. So what are we going to look at for splitting this one? We're going to look at this one, and we're going to go one carbon away, and there's also an H over here. So we're going to look at this one. Okay, so these two are splitting our 1H peak. Now, this is where some nuance occurs. When you are on an sp2 carbon, you're going to do something called complex splitting, which means that instead of saying, oh, we have 2 H's, okay, N plus 1 is 2 plus 1, which is 3, we're not going to do that. Instead, for every unique set of hydrogens, we're going to do the N plus 1 rule at that many times, and we're going to combine them. So this is one set of unique hydrogens. There's only one of them. So our N plus 1 is 1 plus 1, which is 2. Same deal over here. Our N plus 1 is 1 plus 1, which is 2. This is a doublet. This is a doublet. Therefore, you're going to get what's called a doublet of doublet. A doublet of a doublet will look like that. Just 2 doublets together. Don't mix this up with a quartet. A quartet looks like this, whereas a doublet, they're like all the same height. But usually they write it out for you if it's hard to distinguish. Even if it's easy to distinguish, they'll tell you what it is usually. So doublet of a doublet. So this is called complex splitting. Now, why does complex splitting occur? You're kind of lucky. Like, your professors make it simple. Technically, this N plus 1 rule only applies for adjacent carbons that are identical. So for something like this, you know how we did this and we were finding out the total. We had like 1 over here, we had 3, and we had like 2, and we just added all of them up. In the real world, technically, that's not how it works. Each of these would do their own N plus 1, and you'd put all of them together because there's something that is called a J value. And this just tells you exactly how the coupling constants or the splitting works. And it's only simple splitting if your adjacent carbon H's are, identical. Once they're different, their values deviate a little bit and it causes like a mixture of splitting. So according to your professors though, this stuff will average out and it will become simple. So let's do this again. We're looking at this, right? Just do what you normally do, right? We were looking at what's next to it, and next to it, right? Now, these two are identical to each other, these two are identical to each other, and this is its own thing. But these groups that I circled are not all identical to each other, right? Among the different circles. But that doesn't matter because we can just say that their J values and their coupling constants average out, and we can add them up. So we have 3 plus 2 plus 1, which is 6. So our n plus 1 is 6 plus 1, which is equal to 7, which means you have a heptet. So you might be wondering like, okay, when do I do this? When do I not do it? I'll tell you the rule. If you're on an sp3 carbon and you're bonded to an sp3 and you're bonded to an sp3, definitely do simple splitting. So that's what we did right now, right? This is sp3 and so are the adjacent ones, sp3 and sp3. But if you are on an sp2, so literally the example that we did before this is an sp2 carbon, and this is sp2, right? So you're sp2 and you're next to an sp2, you're most likely going to get complex splitting. I have also heard that if you're on an sp3, but you're next to an sp2, so this is sp3, and you're next to an sp2, and either an sp3 or sp2, let me draw both cases actually, right? sp3 next to sp2 and sp2. I've heard from Dr. Tran specifically that these will do complex splitting. Sometimes they'll do simple splitting though, right? Just be aware of both cases. If you're really scared, ask your professor. But these technically should be doing complex splitting. But for sure, the sp2s are higher in likelihood to be doing complex splitting, like when you're on sp2. So like this hydrogen and this hydrogen. So I'm sorry this was very messy. Let's do it again, okay? So let's say we have this. We want to find the splitting of this hydrogen. First of all, there's two of them, okay? It's 2H because there's another one. If we're doing the simple splitting, what can we do? We can look at adjacent. So we have this right here. And we have, I should start doing this in different colors here. These two and that. So what is this? 2 plus 1 and then 1 plus 1. That's triplet, and this is doublet. So this should be a doublet of triplet or triplet of doublet. Doesn't really matter. That's if we're doing complex splitting. If we're doing simple splitting, just put these together. 2 plus 1 gives you an n of 3, so 3 plus 1 is 4. So that would be like a quartet. Now, I keep saying you're probably wondering, but look, they're not going to ask you directly, like, what is the splitting of this? Even if they do, just put whatever, right? But they're going to give you something, like a chart, like, low-key, let me just scroll. They'll give you something like this, right? Where they have it marked, like, oh, this is a doublet or this is a doublet of quartet. If it's a doublet of quartet, you're most likely on an sp2. Not necessarily, but could be. But, like, let's say you have this, right? If you have a doublet of quartet, you can automatically think, okay, I have, one hydrogen, and I must be next to something that only has one hydrogen, and on the other side, I must be next to something that has 3 hydrogens, right? So that's it makes your life easy, right? And then you got to figure out how to make this 1H, so maybe it's like a double bond and then something like that, right? If they gave you like a quintet, I don't know if I have an example here. Let's say they give you a quintet. Don't worry about, am I on sp2 or what? You can figure that stuff out later. Just think, okay, I must be, something that has 2 H's, okay? I have a carbon with 2 H's, and this is a quartet, but let's pretend it says quintet. I must be next to one side that has 3 H's, and then the other side must have like 1 H. Or maybe it's going to be something with 2 H's, and this has 2 H's, right? So I wouldn't worry about exactly when simple and complex splitting happen, because you can still work backwards and figure it out. It's not really like an absolute thing. So if you're still worried, just ask your professor, but it's really not the end of the world. I'm just exposing you to both just so that you can be aware, and not like trip out when you see something like doublet of doublets, but it's not really something to worry about. Okay, guys, let's just like complete this, just because if we're finding the splitting of this, it's going to be 2H, and then we'll just look adjacent, right? So adjacent on the left is 1, adjacent on the right is that. Let's extend this so it's not equivalent. Okay, once again, according to Tran, this would do complex splitting, so I would do n+1, which is 2, and then n+1, which is 2. So I would assume that there's a doublet of a doublet, but it could also just be a triplet if you're doing simple splitting. So yeah, as long as you're aware of the different types of splittings and just how splitting works in general, you're fine. Okay, so a couple more things. If you ever see a peak at 0, just ignore it. That's probably something that's there to calibrate. There's something called tetramethylsilane, which looks like this. These are all CH3s, by the way. This is something that's used to calibrate both C-NMR and H-NMR, and it always shows up at 0. So if you see something at 0, just ignore that. Usually it doesn't show up, but I've seen it show up sometimes. So that's one thing I want to mention. Another thing, you have these values here, but people panic when they see something very off. Like you see something at 3 to 4, right? They'll see something that ends up being like 4.8, and they know it's not a vinyl hydrogen. They're gonna be like, how is this even possible? There's nothing here that matches the 4.8. And like pretend they know it's not this or that. They're like, how could it possibly be this? Just think, okay? These are general ranges, but things can deviate if you have other things present. So let's look at this right here. If you have, let's say you're next to like bromine, and we're looking at this carbon, its hydrogens, there's 2 of them. That will be around 3 to 4. Let's just throw the value like 3.6, okay? But what if you're next to another bromine? Or even this is directly a bromine. Or let's put like oxygen, and then this thing is connected to bromines and stuff, right? This is where de-shielding and shielding comes into play. So de-shielding refers to moving something to the left, and shielding means moving to the right. Now, don't forget, we go increasing order from right to left. So your highest would be about 12. So if you're moving to the left, de-shielding will increase your value. Now, shielding will be decreasing your value. What direction is de-shielding going? Downfield. Whereas shielding is going upfield. So if you have something that's electronegative, it's most likely going to be de-shielding you. If you have more hydrogens compared to other elements, you're likely to be shielded. I would not necessarily use the terms electron donating group and electron withdrawing groups. You can use them just to keep an eye out for like what you're looking at, but I wouldn't use these terms directly, because people think electron donating groups directly mean shielding and EWG means de-shielding. Technically both can cause de-shielding, but let me give you an example of this. If you have, or let's just look at our chart, right? Take a look at this. These are all alkanes, but it seems that the tertiary, which has more electron donating group carbons, has a higher value than something like this. We know that CH3 is an electron donating group, whereas hydrogen is nothing. Therefore, if you use the logic that electron donating groups will protect and shield you, that wouldn't apply here, because clearly it's not working, right? This has to do with electronegativity. Carbon is more electronegative than hydrogen, therefore it has an effect on the HNMR. So the way NMR works is not equivalent to just how regular organic chemistry works. That's why you can't use these terms like that. But what I will say is that knowing electron withdrawing groups and electron donating groups can help you determine which one will de-shield something more than the other. For example, NO2 nitro groups are very, very powerful electron withdrawing groups, whereas an OR group is an electron donating group. This thing generally will de-shield whatever you're looking at, but NO2 will de-shield it more. Now, if you have an instance where there's resonance like that, and let's say you're looking at this hydrogen's peak, because this oxygen can resonate within the ring and just keeps going around, that actually might decrease your value. So move it to the right. So it's not really that big of an issue. It won't be as big of an issue as you might think it is, but I would just know like if something de-shields something more than the other, and definitely know about the carbons being better than hydrogens if you want to go to the left. So once again, if you're comparing, let's do this, okay? If we're comparing this to that, so the red to the purple, both of them are equidistant from the bromine, right? So they're not going to have, neither of them is going to be more or less affected by the bromine than the other. So the only difference here is that the red one has 2 hydrogens, whereas the purple one only has 1 hydrogen. The red one having more hydrogens and less non-hydrogens causes it to be a lower value than this one. Even though, once again, carbons are electron donating, that's not going to change the fact that I just said. This will have a higher value, or like this will have a higher value than these two. So this will be more de-shielded than this one. So now we're going to do some practice. Oh shoot, I completely forgot. Very important formula. Degrees of unsaturation. If you're my student, you already know. You can skip this part. But basically, if you guys have ever heard of saturated fatty acids, let's draw this and then. So basically, a fatty acid that's saturated will be full of single bonds, okay? There's no double bonds other than this, obviously, but they're full of single bonds. Now, why is it called saturated? Because they're saturated with hydrogens. So they have the maximum number of hydrogens that they can possibly have. This one has 2, this one has 3, and this one has 3. But the moment you introduce a double bond, you're no longer saturated, you're called unsaturated. Unsaturated meaning you're not fully maximizing the number of H's you could possibly have because you have to deal with extra bonds. So for example, if we redraw this but we add a double bond in, now we have 1 over here and 2 over here and 3. So in the first example, we had 8 hydrogens. In the second example, we only have 6 hydrogens. So that's 1 degree of unsaturation. So as I just mentioned, a double bond is 1 degree of unsaturation. You also have triple bonds. Triple bonds will be 2 degrees of unsaturation. And ring structures will be 1 degree of unsaturation. So if I have a molecule that looks like this, how many degrees of unsaturation would it have? We have 2 over here. We have 1. We have 2 and 1. So that's going to be 6 degrees of unsaturation. Don't confuse branching with unsaturation. That's completely irrelevant. The only things that will cause unsaturation are double, triple bonds, and rings. Now, a combination of these is a benzene ring. A benzene ring is a ring plus 3 double bonds. So that's a ring a ring plus 3 double bonds. So that's 1 plus 3, which is 4 degrees of unsaturation. If you ever calculate 4 or more degrees of unsaturation, especially if it's more than 4, you should always be looking at the possibility of there being a benzene ring, because they're not gonna be evil. They're not gonna give you 7 degrees of unsaturation and they're all gonna be double bonds or triple bonds. Usually you could cancel out 4 of them with the benzene ring. So I'll definitely look for that. Now, how do you determine degrees of unsaturation with the formula? OChem 1, they taught you this. They taught you 2C plus 2 minus H over 2. This is correct, but there's more to it. It's not complete, and you do need to know the full one for OChem 2. So you're going to add your nitrogens. You can subtract your H's again, right? And you're also going to subtract your halogens. So halogens are going to be fluorine, chlorine, bromine, and iodine. Oxygen is not part of this, okay? O is irrelevant for this formula. Oxygen is not a part of this at all. So you're going to multiply number of carbons by 2. You always add a plus 2. That's just part of the formula. And you add your nitrogens and you subtract your X's. Okay, people mix these up. They flip it. But you're adding the N and you're subtracting X. That's all there is to this formula. Now, if you calculate something like 11.5, if you calculate a decimal, then you did something wrong. Either you miscalculated or the formula is incorrect, because you should never get a decimal. It should always be like a full molecule. Now you're also thinking like, oh, what if I have like sulfur or something? That doesn't matter. Okay, just use this formula. You're chilling. And also, they're probably not going to give you sulfur and stuff like that anyways. Okay. Another thing I want to mention is NO2 is a functional group, right? It's a nitro group. Now, NO2, people don't realize it looks like this. NO2 is a degree of unsaturation because of our double bond. Now, there is resonance within this, right? But that doesn't matter. Resonance does not make a difference, because what is resonance? You're just moving the same single double bond around, right? There's just one double bond, it's moving around. That doesn't change the fact that there is a double bond present. So NO2 has a degree of unsaturation. Definitely remember this, because if you don't know it and you're stuck finding the last degree of unsaturation and the answer is NO2, but you don't know NO2 counts as one, then you're going to be confused. So NO2 counts as a degree of unsaturation. Now, as you can probably tell by this example, oxygen can be involved with being part of a degree of unsaturation. Even though oxygen is not part of this formula, it doesn't matter. I don't know how they came up with this formula, but this doesn't tell you anything. It doesn't tell you what can be or what can't be part of a degree of unsaturation. Oxygen can definitely be involved with that. For example, a big example is carbonyls. This is a degree of unsaturation. You can also cyclize these oxygens. This counts as a degree of unsaturation. Once again, the NO2 thing counts as a degree of unsaturation. So yeah, definitely keep that in mind. So now let's solve some of these molecules out. This first one, you can also do it on your own. You can pause this video if you want. But this first one, we're going to do the degrees of unsaturation formula. So you have 2 times 5 plus 2 minus 8 over 2. So that's going to be 10 plus 2 minus 8 over 2, which is 2, right? 4 over 2 is 2. So you have 2 degrees of unsaturation. Now, I have this chart up here. Take a picture if you need or something. You should have these by now. I don't know why you wouldn't have them. Something like this, but I'm not gonna like include it here. So just keep it like with you or something like that. And we're gonna like figure out what is going on here. So we have 2 degrees of unsaturation. I mean, generally, you probably have like a double bond O, like a carbonyl. Not always, but it's very likely that you're gonna have at least one. So that's something to keep in mind. But it doesn't mean that you're gonna have like, a carboxylic acid. It could just be a regular carbonyl. But I just want you to like think about all these different possibilities, but you still definitely have to confirm them. So let's take a look, right? These right here, they're at like 1 and 2. These 2 peaks, right? So what do we know about 1 and or like 2 and above? If you look I'll just refer back to it here. For now, I'll refer back to it. If you look at this chart, it seems that this type of thing is at like a 2 to like 2.2-ish value, right? Methyl ketone is just something that's like allylic, right? So this thing would be at that range, right? So we have those. So right now, I'm not like fully sure that I have a ketone or like an aldehyde or whatever, but I have a feeling that I might have a carbonyl like that. So I'll just, mark these as like alpha carbonyls. They're both alpha carbonyls, right? This one and that one. Okay. What do I have over here? I have something like 6.1, something around like 7. I see doublet, and I see doublet of quartet. So this is making me suspicious, and I'm thinking that there has to be some alkene. So that kind of makes sense, right? I have an alkene and I have a carbonyl, so that satisfies my degrees of unsaturation. Okay, what else? This one right here, above 6, and also once again at 7. If you look at your chart, let's take a look at it. What do we see? The only thing that matches this, technically this one, but I wouldn't really look at that one. This one, okay? So this is where that whole thing comes up again. This is between 5 and 6. That's what the chart says, but we see something between 6 and 7. Sorry, I got lost. We see something between 6 and 7, and now we're thinking like nothing matches up here. The only thing that matches up is an aromatic ring, but I don't have enough carbons for this. What am I going to do? And they're going to text me and say like, I'm so sorry for failing you again. That's what's going to happen, right? No, keep in mind that there are things that could cause little deviations, like electron withdrawing groups or just some other type of inductive effects. So I'm not going to use that far deviation and say that I don't have this. I probably do have this because that's the only thing that makes sense. So I'm going to start just drawing some stuff. I'm going to draw like I'm going to draw an alkene. Start off like that. Now I want to mention another thing. Actually, it doesn't matter. I'll mention it in C-NMR. But let's just start with like the left side of this. I'm going to use this as like the end of the molecule. We have a doublet of quartets. Okay, what could that possibly mean? It means that we have potentially... Oh, wait, sorry guys. I'm kind of like... I have like undiagnosed ADHD, I'm pretty sure. I just be like thinking many things. Let me tell you something. When I'm working through this, I'm gonna like probably make mistakes because I'm using my thought process. I'm showing you my thought process, so don't expect me to like put the exact correct answer like in the beginning, because that's not how it works, right? Nobody gets this stuff on the first attempt. So it might seem a little messy. I'm sorry if it is, but yeah, let's begin, right? So we got this. I'm low-key tripping right now. I don't know what the hell is going on. I'm sorry, guys. I'm low-key going to erase this because I don't feel confident. What I'm going to do is I'm going to draw my carbonyl in. Okay. Now, these two are alpha carbonyls, right? They're alpha allylic carbonyls. Now, it seems like I have a singlet that has 3 H's. Okay, let's draw something that has 3 H's. That would be a singlet right there, right? This would be a singlet that has 3 H's because there's 3 H's here. And this thing is not going to have another hydrogen just because the molecule will continue. So I'm good on the right side, right? So that is that so far. Okay, what is next? You're probably thinking, how am I going to do this? How can I possibly continue that? The only way I can do that is this. There's something that I left out. This is not just alpha carbonyl. It's just straight up alpha allylic. So this could be something like this. Like that, right? Where you're allylic to just a regular double bond. It doesn't have to be a carbonyl double bond. So I'm not going to panic here and think that like this molecule is cooked, but I'm going to continue this molecule. Okay, what do we do now? Low-key, this is what I do. I just straight up like draw. You know what I'm saying? There's no symmetry. It doesn't seem like there's any like symmetry anywhere. So I'm just continue this molecule, right? We have 5 carbons. Let's go like that, right? Now there has to be a double bond somewhere. Obviously the double bond can't be here or here. So the only places I can put the double bond are like here and here. So let's just do both, to be honest, right? Let's do both and see if one makes more sense than the other. Okay. If we do the left molecule, let's just confirm different things, right? This, I need to see how I'm going to do this. Okay, I'm just going to use letters, right? We have A, B, C, and D. And that's 4 peaks, right? So we have how many peaks? 1, 2, 3, 4 peaks right here, right? What about this one? This says A, B, C, D, and E. So right off the bat, like I kind of already know that the right one doesn't make sense because don't forget these two H's are not identical. So that would mean that I would have 5 peaks, and that doesn't seem like the case here. So it's going to be the left one. But now let's confirm that the left one is correct. Guys, once again, I'm sorry if it looked like I just did a bunch of random stuff. That's literally how I work these. Like, of course, I try to confirm things before drawing them, but sometimes you just draw them out and see if it works. If it doesn't work, you try something else. So now let's confirm, okay? I might be a little off with these peaks. Like, sometimes when peaks are a little... Nah, never mind. Shut up. All right. A, B, C, and D. This is going to be peak A. Why? There's 3 hydrogens. I don't want to draw them here. 3 hydrogens. And the thing you're next to has no H's. Therefore, it's going to be 0 + 1 singlet. Okay, next. 3H doublet. Obviously, it's not B or C because those are 1H. But D is a 3H. Now, is it a doublet? Yes. What are we next to? We're next to... That was horrible. We're next to 1 carbon, and this carbon has 1 hydrogen. And 1 + 1 is 2, therefore we have a doublet. So this is going to be D. Okay, now between... Sorry, I'm dying. Between the other ones, we have doublet of quartet and doublet. First of all, they're both 1H's, and they're both in the vinylic range. Vinylic meaning right on the double bond, or the sp2. So it doesn't matter if I know which one's B or C. I think this molecule is done, but let's just confirm it anyways. Letter C, this has 1H. What are we next to? To the left side, we have 3 over here. So that's an N + 1 of 4. And to the right, we have 1H, which is an N + 1 of 2. Once again, I'm doing the N + 1 twice just because we're on an sp2 carbon. So that's a quartet of a doublet, or a doublet of a quartet. So that tells me that this is going to be C. And the last one would be B. Let's just confirm it real quick. B is connected to the left, and it has 1 over here. So that's N + 1 = 2, a doublet. And to the right side, we have nothing. So it's just a simple doublet like that. I hope this made sense. So that is our answer. Let me draw it again. Now, if you're wondering, do I draw it cis or trans? I don't really know, bro. Obviously, they're going to show up a little differently, but that's beyond your scope, so don't worry about that. They're fine. All right, next one. We're going to always start with the degrees of unsaturation. So 2 × 6 + 2 - 12 over 2. That's going to be 1. And, you know, once again, this could be either a double bond or a ring. No triple bonds, no benzene. So we'll figure that stuff out. What do I notice? I notice that we obviously have some symmetry, right? Because there's 6H. Like, obviously, like, the maximum number of H's a carbon inside of a molecule can have is 3. So if the fact that there's 6 means that there has to be some sort of splitting or branching. For example, like, if you branch like this, these are identical. So I think there's something like that going on. I also kind of know that this is the case because of this. Do you see that? It's a 1H septet. That's literally this, because the 6 H's, they're next to this, which is just 1H, right? So that's going to be N + 1 of a doublet. Now, this 1H septet looks like the green hydrogen because you're next to 3 over here and 3 over here. They're identical, so 6 is your N and + 1 is a septet. So yeah, I know that type of branching has happened. So I mean, I can even just, yeah, let me just start my molecule like that. I'll start like this. Okay, And you know what? Let's already... Nah, it's fine. Okay, I was going to say we can mark them, but we'll just leave it for now. So now we're trying to find this 2H quartet, and we're also trying to find that 3H T. We still need to find our degree of unsaturation. So take a look at, your chart and see what this could possibly be. So I am just going to assume that there's a carbonyl, and the reason for this is because I don't think there's a double bond. The reason for this is I would most likely have a vinylic stretch. If you disagree with me, or if it doesn't make sense what I'm saying, you can even attempt to draw the molecule out, right? Once again, I don't want to draw out all of my thoughts because it'll take so long, but just draw, okay? If you have the slightest, if there's a slight possibility that there's something you're not really sure, just draw it out, see if it works, okay? I'm telling you right now, the vinylic thing would not work here. Vinylic, once again, meaning that. So yeah, also, you might think what if you have something like that where there's no H's on the vinylic? I'm telling you that's also not going to work because this takes 6 carbons to do, and we only have 6 carbons, so there has to be at least one vinylic hydrogen, and we're way too low, right? It's supposed to be 5 to 6. Our range ends at 5, so it's not going to be shielded that much either to 4. So yeah, right? Also look at this. There's 2H. Your vinylic should not have 2 hydrogens. It only should be 1, right? So that's how I know that the only other thing that I could possibly have is a carbonyl. So I'm gonna just write that. That's my thing, right? That's my degree of unsaturation. Now, what do I do with this oxygen? There's 2 of them, right? And I'm determining that one of them is going to be part of the C double bond O. The other oxygen, right? Oxygen only shows up in 3 ways. Either as a C double bond O, as in ether, or as in alcohol, right? We don't have an alcohol because the alcohol stretch is going to be very high. Actually, no, sorry, it wouldn't be high. Alcohol specifically will be between 2 and 5, but the thing about alcohol is that it's going to be 1H, right? And so we don't have any remaining peaks that are in the 2 to 5 range that are 1H. The only one we have is this one, but there's 2 things wrong with it. Number one, we already determined what it is. The second one, shit, man, I just realized I forgot to say something. Okay, we're going to come back to this, and I'm going to tell y'all. So back to the topic of splitting. We talked about how splitting works, but something that never gets split is OH and NH2. So you're looking at the peak of this, right? The peak is going to be 1H integration. Now, we normally look at what we're next to. Okay, we're next to here. We have 2 H's, n plus 1 equals 3, triplet. No. That's not how it works. This is only going to apply to carbons. So OHs and NHs will never be split. These will always be singlets. They're always going to be singlets. That's one thing. Now, another thing to know is that these will never split things. So if you're looking at this peak, you have 2H. And you're trying to figure out, okay, to the left, I have 3 of these, so that's n plus 1 equals 4. Over here, I have 2, so that's 2 plus 1 equals 3. No. This will never split. That's the same for the OH. So NH and OH never get split nor cause splitting. Okay. So with that in mind, we know that there is no OH, okay? And for sure, we don't have a carboxylic acid because carboxylic acids are going to be 10 to 12. And the highest peak we have is right above 4. So I may have an ether. And I probably do, but I can just, for simplicity, connect it to my ester. Or my carbonyl to make in this. In ester, right? An ester has a carbonyl portion and an ether portion. So technically I can have a ketone and then an ester. But usually they don't do that. I mean, I wouldn't rule out this possibility. First, confirm it. But just from my perspective, I'm just, I just assume things and then try them, right? So I'm assuming that there's an ester instead of a ketone and an ether. So I'm going to pursue the ester. If it's wrong, it's wrong, and I'll just do the other one, right? So let's do that. I'm going to draw my ester. And, I'm going to automatically put a carbon here because it can't be an H. As for the left side, I also will put a carbon because if there's a hydrogen here, like if it just ends, then I would have like an aldehyde peak, which is at 9 to 10, which we don't have. So I'm going to just do this, okay? So we used 3 carbons. We satisfied our 1 degree of unsaturation. Now we got to figure out where the other 3 carbons are. And we know that there's something like this going on. So I low-key just feel like it. I feel like doing this. Just testing it out, right? So we use 2 carbons there, and we're missing 1 more. So I'm gonna do this, okay? Let's just see if it works. First off, we already figured out the purple ones that I circled, okay? Now the 3H triplet, where could that possibly be? Let's take a look. The 3H triplet is probably gonna be this. Why? There's 3 H's here, and you're next to 2 H's, so that's a n plus 1 of 3. So I'm gonna just circle this to say that we found it. And the last one is a 2H quartet. So this is 2 H's. And we're next to 3 H's. So 3 plus 1 is 4. Okay. Now I hope somebody is screaming at their phone or computer screen saying, "You're stupid and you're wrong." Because you're correct. I did make a mistake here on purpose, once again to show that I don't get the answer correct the very first time. The issue here is that this peak, this supposed quartet, is not in the right position. If it's alpha allylic, so it's allylic to this, or like the methyl ketone thing, it should be about 2, okay? Even if it gets de-shielded, like the maximum would be like 3.5, right? I can't see it going all the way above 4. What causes something to be at 4? I'll just pull it up. Look. If you're next to a halogen or an oxygen, okay, that would cause it to be 3 to 4. So we do have that possibility, but right now it's being taken by this. It's being taken by this. And what is this thing at? It's at around 2 to 3. So it looks like I flipped it. This thing should be over here, and this thing should be over there. So all I'm going to do is just flip the substituents. I'm going to draw it again and flip it. So we got that. This time I'm going to make the ethane or the ethyl group as part of the oxygen, and this will be, I hate when that happens. Okay, this isopropyl thing will be part of this side. So now everything matches up, and this is our final answer. Okay, next one. Okay, degrees of unsaturation, we got 2 times 10 plus 2. I'll just go in order. So minus the H's, which is 12, minus the chlorine, and plus the nitrogen, all of that over 2. What is this? 22, 10, and 10, 5. Okay, so it's going to be 5 degrees of unsaturation. Automatically, I'm going to say there's a benzene, okay? I'm going to say there's a benzene, and I'm going to prove it. I'm going to prove it with this peak right here. It's at 8. Just take a look at our chart. Guys, this is the last time I'm going to scroll up. After this, just pull it up on your own, and I'll refer to things, but I'm not going to literally point to it. So we have I already circled it, I guess, but this thing right here, right? 7.2, okay? That's all I care about, right? I don't really care if it's at 8. As long as it's close enough and I have more than 4 degrees of unsaturation, I think I'm fine. As I mentioned, look, it literally says right here, it's approximate. There's probably something causing it to be de-shielded, and that's why it's sitting at 8. And as you can see right here, I have an NO2, so that must be playing a role. I also have a chlorine, so I'm fine. I'm satisfied. I'm confident. I know it's going to be a benzene ring. Okay, so we have a benzene ring, and the only peaks that we have for benzene are up here, right? So that must mean, well, first let's just draw the benzene, okay? Let me erase this. I have a point I'm trying to make, but let me just draw it. Okay, we have a benzene. Now, there's only one peak and there's only two H's. How many H's are in a benzene? There's 6 total H's just off the bat. Obviously, once you start adding stuff, then you decrease it. But there's only 2 H's that are being represented by the benzene. And these 2 hydrogens happen to be identical. So that means that 4 of these benzene carbons are going to be occupied by some substituent. And 2 of them, let's box these, 2 of them will be remaining. But those 2 have to be identical, which means that if we place substituents all around, they have to be placed in such a way that we can make the molecules symmetrical. So that's what I noticed from this. So we'll start over. Let's draw this benzene. Okay. Now I use 6 carbons and I need 4, right? So the only oh, you know what? Sorry guys, once again, the ADHD, I was thinking a bunch of things, but let me make sure I'm verbalizing it. I already feel like there's going to be some ethyls involved, but I'm not going to draw them yet because first I'm going to draw the NO2 because I need to satisfy that 5th degree of unsaturation. Let me take a sip of water real quick. So I'm just going to put it up here straight up. Right now I still have symmetry. I can base things around the NO2. It doesn't matter. So there is that. And NO2 doesn't have any peaks on C-NMR or H-NMR, so I don't have to worry about that. And this kind of confirms why we have this right there. You know what I'm saying? The NO2 is very de-shielding. It's very electron withdrawing, so it's going to cause that peak to be very high up, more than 7.2. Okay, so we got that. Now we got to find out where the other 2 carbons are and the Cl. Now, the reason I know that there's going to be 2 ethyl substituents is because the chlorine can't be part of it, right? Okay, first of all, we have 4 carbons, right? C4. If you want to maintain symmetry, then some of your substituents have to be the same. You can't make a 3-carbon substituent and then a 1-carbon substituent. There's no symmetry here. You can't do a 2-carbon substituent and then 2-carbon with a chlorine. There's no symmetry here. So the only way that you can use these last 4 carbons and maintain symmetry is by having them split in half. So C2 and C2 and placing them as ethyls. So we have ethyls like that, and chlorine must be by itself because it can't be part of the ethyls because then those won't be identical. Now we just got to figure out where we're going to put it, right? I put it here on purpose because now we have some symmetry, right? So these 2 carbons that I'm pointing at are indeed identical. But now the issue comes up, okay? Is the molecule this or is it going to be like that? You know what I'm saying? First of all, let's just confirm that everything actually makes sense. So we already figured out what the 2 H's are, right? It's going to be one over here and one over here, right? In this case, it's the same thing, one over there, one over there. Now, what about the 4HQ and the 6HT? This is going to be, let me look at it. It looks like a symmetrical ethyl just off of this, right? The 6HT is going to be the 3s on both sides. And they're both next to 2, right? So 2 plus 1 is 3. Same deal over here. You're next to 2. So that's going to be this one. Sorry, let's do blue. And then the purple ones are going to be 2 plus 2 H's, which is 4. And they're next to 3. So 3 plus 1 is 4, making it a quartet. And same deal over here, right? I'm not going to draw it again. So both of these molecules are good. The only thing we're trying to figure out is okay, which one is correct? The only difference between these 2 is where the hydrogens are placed, as well as actually just everything, to be honest, right? So what I would do is just look at how much things are varying, how much things are being de-shielded or shielded. So first off, I'll look at this. This is in the benzylic range, right? If you look at your chart, you're going to see something that says PHCH3, and it's about 2.3. Okay, so that peak, where exactly is it? It looks to be right there, right? we'll just be generous and call it 2.5, even though 2.5, actually, I'm stupid, sorry. This is 3, right? So it definitely did increase a little bit, but this is 2.5-ish. So we'll say that it's sitting at like 2.7, even 2.8. We'll be a little generous right there and say 2.8. Okay, so we went from an estimated 2.3 to 2.8. Now, part of that increase could also be coming from the fact that there's a carbon here. Okay, the other thing that contributed to this increase obviously will be the NO2 or the Cl. It doesn't have to be right next to it, but in close proximity would cause that. Okay, now I'm already thinking that this is not that big of an increase to where I think something as strong as NO2 would be playing a role. Cl is pretty electronegative. It's the third most electronegative element, but in terms of electron withdrawing effects, NO2 is like way better. So that's one thing that's making me think that the second molecule is correct. Now let's just look at the aromatic one. The aromatic one, it went from 7.2 to 8. This is like a bigger jump, and there's nothing else really causing this to happen. It must be mainly more due to the NO2 or the Cl effects. So since the benzene stuff increased a little bit more than the CH2 did, I'm just going to go with that the second molecule is correct because these H's are closer in proximity to the NO2. And obviously, I know this must be playing a role in that, but it seems that the aromatic H's, this thing, had a larger shift than than these two did. So that's why I'm treating it like this, where these two that I'm circling are closer to the Cl, which has a less prominent effect, compared to this, which is close to NO2, which has a stronger effect in terms of deshielding. I really hope that made sense because I don't know what the hell I just said. So to keep it clean, we'll draw the molecule again. And guys, if you draw it the first way, like whatever, they'll probably take some points off, but not that much, right? It's like a lot of partial credit just because you flipped it on accident, but you had everything else correct, right? So this is what I would say the final molecule looks like. Matches up with the CHEM. Okay, last one we have C10H20. So that's 2 times 10 plus 2 minus 20. That's going to be, over 2, that's 1. Okay, so obviously, actually not obviously, we either have a ring or a double bond. I was gonna say obviously there's a double bond. I feel like there's a double bond, but we'll see what happens. Another thing I see is that there's only 3 peaks and there's like 20 hydrogens, so that's kind of crazy. There's like a lot of symmetry going on here. So I wonder what that could be about. I guess I will point out this thing. If we look at the previous example or the two examples ago, when you see something like this where you have like a septet next to, or not next to, but a septet and a doublet, and they're like in like a small area like below 3, that probably means that you have like an isopropyl group like that, where this thing is going to be the septet and these two will be the 6H doublets, right? So that's 1 septet, 6 doublet. Now look at this. This is 2 septet, 12 doublet. So initially I had 1H septet and 6H doublet. Now I have double that. So not only do I have this branching, I have it twice. So I must have like 2 of these, and they must be placed in a manner that makes them symmetrical. Otherwise they wouldn't be the exact same peaks. So I already knocked off like 6 out of the 10 carbons. Okay, cool. Now, what else? If I knocked out 6 out of the 10 carbons, that means I'm left with 4 carbons. And those 4 carbons are not going to make a ring. Like, you're not going to have this. I mean, you can try it. I don't think it should work for this. But I'm just saying, you know what I'm saying? It shouldn't work. I'm too lazy to check it, but it shouldn't work. You can still try it though, but it doesn't make sense because usually they wouldn't give you a 4-membered ring. So what does that mean? I must have a double bond. So I'm going to draw an alkene. And let's just put these in like that. So how many carbons is this? That's 8 carbons. Okay, now I have 2 more. Obviously, like, I have to add it over here, because if I were to add it anywhere here or there, I would be like ruining this thing that we just made, the isopropyls that are symmetrical. So I'm putting it over here. Now let's see if this actually works. If we look over here, we have a 2H septet and then the 12HD, right? Now they're very far apart. The 12H doublet is like below 1, which is in the like straight up just alkane range. And that makes sense because these two are not like allylic to this. This is allylic. So we would expect this thing to be higher, but these two and these two, which are identical, so the symmetry, they're far apart from this thing. So we're gonna add all of those, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12H, and all of them are close, or they're adjacent to just this, which has 1H. So their n plus 1 is doublet. Okay, so 12H doublet makes sense. We'll circle it because we're chilling. Why did my Apple Pencil die? Guys, my Apple Pencil died. That sucks. Hold up. Okay, I'm using my finger. So anyways, next we're gonna do, I'm drawing blue. So obviously this and then that, they're identical. So there's gonna be a peak that's 2H, and they're next to this and this, right? Both of them are next to 6 identical H's. So in either case, the n plus 1 will be 7. So that means that we're going to get a septet, and we see that over here. Now the peak is, close to like 2.5, and that's fine because if you take a look at where they are, they're allylic, right? They're alpha allylic, which means that you're going to have a value of like 2.1 to 2.5. So that matches out. Circle that. Lastly, we're left with 6H singlet. Now the 6H singlet has to be these, and let's take a look. They are identical, and there's 6 of them. And what are these adjacent to? Adjacent to something with no H's, right? So your n plus 1 is 0 plus 1, which is a singlet. So that means we have a 6H singlet. Now looking at the value, these are also considered like the alpha allylic. So we expect something around 2.1. These are a little bit lower, but not anything crazy, right? This is 1.5. This is like 1.8. So close enough. So that matches out, right? It's definitely not just like a regular alkyl group. So we confirmed it. Therefore, our answer is that. So we'll draw it again just to make it look nice. Our final answer would be this. Now, same deal here. I don't know if cis and trans really matters, but I think, I don't really know. I don't want to say anything wrong, so I'm not going to say anything. Let's say the answer had to have been trans, but the answer was cis, but you put cis or vice versa. Barely any points off, right? If you're paranoid, confirm with the professor. But yeah, let's move on. That was fun, I guess. C-NMR we're going to zoom through, and I don't have any practice examples because it's just like H-NMR, but a little bit simpler. With H-NMR, we had integration and we had the splitting, right? So when it comes to C-NMR, there is none of this stuff, okay? There's none of this. We have absolutely none of that. One more time. We have no integration, no splitting. Whenever you look at a C-NMR spectra, see if I have an example. Take a look at this. This is all you're going to see, right? Just lines. I could have just drawn that myself. So all you're going to see is this, lines. And the values are going to be greater than what you expect on an H-NMR. You're going to go from 0 to 200. But you're going to see like lines. We're not going to know how many carbons correspond to each line because there's no integration. We're not going to see any splitting, so we don't know like what we're adjacent to. All you see are lines. Now, what I would take away from C-NMR, obviously, as you can see by this picture, we can figure out different functional groups approximately by our values, but we can also figure out symmetry, right? So if you have a molecule that's C12H15 or something, and you have a C-NMR that has like 2 peaks, then that means there's a lot of symmetry because there's 12 carbons and all 12 carbons are being resembled by 2 peaks. So that means that some of these carbons have to be identical to each other. Now, as for if there's 6 over here and 6 over here, or 9 and 3, that you can't directly tell from a C-NMR. So you have to use other clues, right? Either other charts or just trying out the molecule or seeing where the peaks are, looking at degrees of unsaturation, etc. So yeah, that's pretty much it for C-NMR. It's just like a simpler version of HNMR, just an extra tool. Same deal over here, where if you have something at 0, it's just the TMS, the tetramethylsilane. Just ignore it, doesn't correlate to anything. I guess something else I want to mention that could go for HNMR or C-NMR. If you look at some of these peaks, like let's look at okay, you see this right here and like that. So they overlap, obviously, like the overlap is here. And so a big question people have, what is this range? Hold on. It's like, we'll just call this 40 to 60 and then the bottom one 30 to 50. People are like, okay, if I have something that's at like 45, which one is it? Is it this CH3 alkyl group, or is it an alcohol, or is it ether? What is it? Because they're both in the same range. Or what if I have 2, or like, what do I do? So first of all, as I keep saying, there's other things that will help you out. Let's say there was an alcohol present, you'll probably get like an IR that shows an alcohol stretch, or maybe you'll get an HNMR that has an alcohol peak. Another thing, like, if you have both of these present, what I will tell you is that this one will be higher than that one. So let's say you have 2 peaks, one at 45 and one at like 39. The 45 one should correspond to the carbon that's bonded to the alcohol, whereas the 39 one would probably be like the regular CH3. So that's what you can take out of this. But as far as knowing exactly which one is which, it shouldn't be confusing. Like, don't have to worry about them overlapping that much. Okay, same thing applies to the HNMR. Like, for example, yeah, I guess like methyl ketone and acetylenic, right? Like these two, they just give you one value, but they overlap technically because they just give you an approximate value. So they overlap. Obviously, as you know by now, you use other clues. So you wouldn't just see a value at 2.5 and be like, oh, that's a triple bond hydrogen. Or you see 2.1 and say, oh, that's automatically an alpha ketone. It could be something else. You have to look at the other clues. So that's what I want to mention about C-NMR. So I don't have any practice for C-NMR because it's just HNMR. Again, the concept is the same, but we will do some C-NMR stuff like afterwards when we combine everything. But let's move on to mass spectrometry. So I kind of want to zoom through this because it's more about like practice than explanations and stuff. But basically, mass spec. Okay, let's draw a molecule. This molecule, I feel like I'm dumb, but it should have a mass of 88. Okay, so if you see this molecule in a mass spec, you're going to have a peak that's called the M+ peak. This is called either the parent or the molecular ion peak. It's going to be at 88. The x-axis is M over Z. I will get into what that means in a second, but essentially the simple answer is just mass, okay? So on a mass spec, you're going to have a peak there. Now, you're also going to have a bunch of other peaks like throughout, right, at different masses. Some will be high, some will be low. If you have something that's tall, like let's just draw this being tall, that would mean that it's very stable. If it's something low, then it's unstable. But why do we have all these peaks? Because when you throw something into a mass spectrometer, you're going to basically have it just shoot a bunch of different missiles at this molecule and mangle it, okay? So you're gonna break it up and produce many different fragments, and each of those fragments will be tested for their stability, and depending on their stability, they're gonna show up either as very tall or very short or even non-existent. So what do I mean by fragments? Let's cut off, let's just cut off this right here. Actually, we'll do it like this, okay? We're gonna cut that off. When you fragment the molecule, you're producing both a cation and a radical. So you can choose which side becomes a radical and which side becomes a cation, and both can occur. But for simplicity, I'm gonna make the right side become the cation and the left side will become the radical. So when I cleave this, I'm going to get this right here. A cation right there and a CH3 radical. Now, both of these were produced, but this is the thing that I am looking for in the mass spec, because mass spec, now this is where we can get into the x-axis, mass spec is mass over charge. So let's just say the mass is it's going to be like 73. Okay, the mass is 73. The charge is over 1 because look at the charge of this molecule. It's just a +1. So that is the case of like all of mass spec pretty much, at least for us, that the Z, the charge will be 1. So what I like to look at the x-axis as is just mass. So it is m over z, but you can just think of it as mass. Now there are instances where the z will not be 1, but that's beyond our scope, so don't worry about that, right? But I want you to know that it's m over z just so that you know that you're looking at the cation and not the radical. So we have this molecule, right? Okay, the mass is 73 because I removed a metal. I removed a CH3, which is 12 plus 3, which is 15. So I did 88 minus 15 to give us 73, right? So this has a mass of 73. Now let's put 73 over here. Let's say 73, this molecule is low-key unstable, then, or let's say it's very, very unstable. It'll look like this. In this case, it's actually very stable, which I'll explain in a second why, but this will be very high, okay? Forget this stupid peak. It's going to be very, very high. Now, why is this? This is a primary carbocation. Yes, it's primary, okay? People think it's secondary because they're connected to two things. That's the OChem 1 rookie mistake. This is primary because primary, secondary, tertiary is number of carbons you're bonded to. We're bonded to one carbon only. But this is actually primary allylic, and it's very good because the oxygen has resonance. So you can do resonance and get that, right? So because this is a very stable molecule, it's going to have a very high peak. Now let's do a different type of cleavage. Let's just say we cleaved like that. So then we would get we'll make this the cation and the ethyl will become the radical, right? Once again, this can happen where this is the radical and this is the cation, right? Doesn't matter. But we'll just do this for now. We'll call this the cation and this the radical. So we removed a mass of 29. We removed an ethyl. These patterns are, if you know them, it makes it easier, right? Like removing a methyl is minus 15. Removing an ethyl is minus 29. I'll mention a couple others in a second, but minus 29 means we have a mass of 59. So what is this? Is it pretty stable or not? It's really not that stable because it's a primary and there's no allylic stuff. Technically, we have another electron donating group here, but it's not that big of a deal. So we'll call this low-key unstable, and it has a mass of 59. So let's go at 59 right here. We'll just draw like this, okay? Nothing crazy. So that's pretty much the essence of this. You know what I'm saying? It's about the cation stability. But now I do want to mention that radical stability is technically important as well. Like it's kind of hard to give examples and draw it out, but in a ranking question, they might give you a question where it's like this, like a fragment. I'm using the same molecule, by the way. We have a fragment that, let me give a different example. Give me 1 second. Okay, let's take a look at this, right? They're going to say this is our parent molecule. and they want you to rank like 5 different fragments. One of the fragments will look like this, and the other fragment will look like that. So both of these are identical in the sense that they're both primary allylic, right? They're both primary allylic. So how do you determine which one is more stable, right? They're both going to have pretty high peaks on the mass spec, but which one is more stable? Now you have to look at the radical stability. So for the right molecule, or the one on top, we cleaved off this thing, right? So we cleaved off like an isopropyl. So our radical looks like that. For the left molecule, or the bottom one right here, what did we cleave off? We cleaved off this. So we cleaved off just a N-propyl, like that. Which one is more stable? This one is more stable because don't forget, radicals are similar to cations, where more substituents is better than less carbon substituents. So this is secondary and this is primary. And once again, since these are both primary allylic, we look at the radical stability as the determining factor. So this one is going to be ranked higher in stability than this one right here. So first, step 1 is look at cation. Okay, if you have a better cation, you're done. Don't worry about the radical. But if they are the same, if same cation classification, then you look at the radical stability. That's what I want to say for this. Now, mass spec, like once again, it's kind of like, I mean, I think y'all have experience with this. I'm just like trying to explain it from scratch, but basically like they're going to give you something like this and they're going to ask you like which mass spectrum corresponds to which molecule. Basically, like in general, I just want to tell you, whenever you have a molecule with an alcohol, so we'll just draw the same one again, the most stable fragments will always be through something called an alpha cleavage. So an alpha cleavage refers to this. Look, alpha is a thing of, it's like a point of reference. You have alpha, beta, gamma, other stuff. These are reference points, okay? When we say alpha, we're saying with respect to oxygen. So the atom that's alpha to the oxygen is this white carbon right here. Alpha cleavage means you cleave any bond from that alpha carbon. Obviously not this bond though. So you can cleave this one or that one. And both of them will be very stable. One might be more stable than the other, but in general, they're both very, very stable. Why is this? Let's do both of them. Let's cleave the left one. I mean, you already know because I already gave it away. But we have that. If we cleave the right one, we're going to get... It's because of this, the allylic, the resonance, right? You can resonate. And same thing over here, right? You can resonate with the cation. So I would always look for these, right? If you have an alcohol, I would always look for these, and whatever mass you end up getting from these alpha cleavages, look for that on your mass spectrum and see if you actually have a peak that's high, then it likely is that molecule. If you don't see anything or it's a very low peak, then you might be looking at the wrong molecule or the wrong spectrum. So that's something to keep in mind. Let's say you had a molecule that looks like this, and they're asking you to find the peak that has a mass of like, let me calculate this real quick. A mass of 42, okay? And you already tried your alpha cleavages because they're very stable, but they didn't work. Look for other places where cations can be stable. Don't forget tertiary is better than secondary, is better than primary. I see a big opportunity for a tertiary carbocation. So I'm gonna cleave like, well, I'm kind of stupid, right? That's not even tertiary. But anyways, right? We'll cleave that and we ultimately get this. And I mean, secondary is whatever. Let's just pretend this is very stable. This is 42 because you have 1, 2, 3, 4, 5, 6, right? 36 plus 6 is 42. Guys, I'm stupid. Anyways, you get the point, right? Just look for other places where you might have stable cations and try to find those peaks on your mass spectrum. If they're there, you're probably doing something right. If they're not there, maybe you're doing something wrong. Another type of peak to well, actually, to add on to this, this is very, very stupid, but look at this. Alpha cleavage in mass spectrum also applies to carbonyls, and it's the exact same thing, okay? This carbon, you cleave to the right or to the left. If you cleave to the right, you'll get this. Now, I know exactly what you're thinking. This is very unstable because it's sp2, and you don't like resonate if you're on like a vinylic carbon. And normally I would agree with you, but for some reason in the mass spectrum world, this actually does resonate and it forms this. It's so stupid. Take a look. It forms this right here. Obviously, we'll draw it linear, right? But it does something like this, making it stable. It's so stupid, but alpha cleavage applies to both alcohols and carbonyls, even though you might disagree. It's just, it works, okay? So look for it in both of these cases. Now, one more thing for alcohols is that they can do something called a dehydration. And dehydration causes a mass decrease of 18. So if we look at this thing again, dehydration will just be forming a double bond, right? So you're going to lose an OH and like an H from wherever you can make a good stable double bond. And so your mass, or your fragment, sorry, would look like this. Now, something that nobody realizes is you can cleave once. Everyone knew this. That's one thing you can do. But you can dehydrate and cleave. And it makes sense because this doesn't even have like a charge, right? Like you can make a cation if you need to. And so that's exactly what you can do, right? We cleave, we dehydrated, and now we're going to cleave it. We're just going to cleave this bond, and you're going to make that. And this is really stable because it's allylic. Right? So that's what I want to mention. In this case, right, you would get a mass decrease of 33 because you dehydrated and you removed a methyl, so that's 15 plus 18, which is 33. So something to keep an eye out for. Please don't do this where you try to dehydrate a carboxylic acid. That only works for regular alcohols. I don't even know how you would do this because you need a hydrogen nearby and you don't have one right there, so it wouldn't work, right? So one last thing is that we talked about this M plus peak, but there's also something called an M plus 2 peak. It has to deal with like isotopes and stuff like that, but the M plus 2 peak is important because it can tell you about the presence and type of halogen, if there is one. So this is how it works. If you have an M plus peak and then you have an M plus 2 peak, that's like a third. Let's say this is like a third of the M plus peak. That means that you have a chlorine. If you have an M plus peak and then you have an M plus 2 peak, that's 1-to-1 with your M plus peak. That means you have a bromine present. And then there are like other things, like I heard you can figure out if there's like a sulfur and stuff like that with M plus 2 and M plus 1 and stuff like that, but that doesn't matter, okay? All you need to know is chlorine and bromine. So one more time, if it's a third, it's going to be chlorine. If it's 1-to-1, it's going to be bromine. So now, give me a second. I feel like I always forget something, but I think it's fine. So now we're going to start with some questions. So in this question, we have to figure out which molecule corresponds to which mass spectra, and there's three identical, they're all like the same weight, right? The same formula. So we gotta see what we can do. I guess something that I remember that I forgot that I want to mention real quick is that the tallest peak on your mass spectra will be called your base peak. Don't forget, this is the M plus, or the molecular ion, or the parent peak. That's the one that is a peak that corresponds to your molar mass. And I guess we can just talk about it real quick. We don't see an M plus 2 peak or anything at all because there is no halogen. Okay, so this is our base peak right here. Now, the base peak is supposed to correspond to the most stable fragment, which I guess could also include radical stability. But sometimes you might disagree. Like, you might be choosing between like this and that. Let's say this is option A and this is option B. Option A is more stable because it's secondary and it resonates with an oxygen, whereas B is just primary and it resonates with the carbons. There's also missing octets no matter what resonance you have. So you might think like A is the more stable one, so it has a higher peak, whereas B has like a little bit lower. But it might be flipped, like B might end up having a higher peak and A doesn't. Sometimes these things don't make like perfect sense. There's like other factors involved. All I will say is like, if that's the case, it's whatever. But one thing that should be certain though is that if you do have a base peak, even if it's not what you think is the most stable fragment, it should still be a stable fragment, right? So if B was the most stable fragment, that's fine because it's still an allylic fragment. But if you looked at something like this and this was your most stable fragment when you had these available, then something is off. Like that shouldn't be the case because you're comparing a primary to like resonance stuff. So that's just, yeah, that's what I want to mention. Now let's go ahead and figure this out. So our mass is 136 and our most stable, supposedly, peak is at 91. So it means we lost 45 grams per mole. You know, I don't really know exactly what this is because the first thing I thought is like an isopropyl, but this would be a mass of 43. So that must mean that there's like an oxygen involved. That's how I'm logicking out through this. So I need to remove something with an oxygen and probably 2 carbons because oxygen has a mass of 16 and carbon has a mass of 12. So if you add 2 of them, that's 40. And there might be enough hydrogens to get me to 45, right? That's how I'm thinking about it. So option A and B, like the first two, they look like I can do something like this. For the first one, if I cleave here, I get what I want because I'm removing 2 carbons, so C2. How many? There's like 5 H's and O. And I'm also making this fragment right here, a benzylic carbocation. So that seems like it works. I can do the same thing over here and form a benzylic carbocation, and I can remove what C2H5O. And if we add that up, right, 24 plus 16 plus 5 is 45. So both of these would give me that base peak. Now, same thing, okay, once again, I know that benzylic technically should not be as good as allylic with the oxygen, but it doesn't matter. Benzylic is still very, very stable. So now what do? I'm going to look at another peak. I'm going to look at another tall peak. It seems that 31 is standing out. That must mean that I can make a fragment for one of these to get me a peak there that's stable, right? So let's try the left one. So 31 means that my fragment should have like 1 carbon and 1 oxygen because 12 plus 16 is 28, and then maybe I'll have like a couple hydrogens. So I can only have 1 carbon. I can only fit that much. I can't really make a fragment here. Hold on, let me erase these. I can't really make a fragment here that gives me just 1 carbon and 1 oxygen. The only way I can do that is by cleaving twice. So if I cleave over here, I have 2 carbons. If I cleave over here, I have all of this. So that's not going to work. So then I'm going to look at the second molecule. I can do that because I have a primary alcohol. So I'm going to do an alpha cleavage right here. And I'm going to make this. And this is pretty stable because of the resonance. So what is the mass of this? It's 12 plus 16. And how many H's do I have? I have 1, 2, 3. So 28 plus 3 is 31. And that matches to this peak. So I know that the first molecule will be the first answer will be the second molecule. Okay. Now let's do the second one. They didn't mark the base peak, and I mean, they is me because I made this, but I don't know what the base peak is. I see a significantly tall peak at 45, so I'm going to see if I can do that. So using my amazing math skills, I know that this must be 2 carbons. Wait, I just realized we already figured out what a 45 is. So 45, remember when we went for the 91 peak, that meant we had to remove 45. And what did we figure out was 45? It was 2 carbons and an oxygen, and then however many, what, H5, right? So this time, instead of making this thing the radical, I'm making this the carbocation fragment. So how do we do that? I mean, you know, we have either option 1 or option 3. Option 1, we already did it, right? Option 3 doesn't even work. We can't make a 2 carbon molecule fragment, because if we want to detach from the benzene, the only way we can do it is like this, and you would be ending up with a 3 carbon plus oxygen fragment, which is way too much. So we're gonna cleave over here and make this the carbocation. That would give us this, and I tricked myself. Yeah. Anyways, making this a carbocation, and we already calculated this, right? This is a mass of 45, and this is stable because of resonance. So we should expect a tall peak, and we do have one at 45. So that's our answer, right? The second one is going to be that. Leaving us with the last one just by process of elimination, we're going to get this. We can just go ahead and try and get 107. Don't forget the mass was what? It was 136, and we're trying to get to 107. That means we lost 29. Losing a mass of 29 corresponds to losing an ethyl. So that makes a lot of sense here, because if you do an alpha cleavage, you would get that, right? You would lose this C2 H5 molecule or fragment. So this is good. We have completed this this question. Okay, now let's do some common ranking questions just so you can be familiar with like terminology and whatever. So this first one is ranked by number of signals in a spin decoupled 13 C-NMR spectrum. Whatever, spin decoupled 13C, nobody cares, whatever that means, right? It's just C-NMR, they ask for a number of signals, so you have to look at how many peaks would show up, right? And remember, symmetry can decrease the number of peaks. So let's just take a look, okay? So these two are, this molecule is just 2 benzenes together. Just because there's 2 double bonds here and there's 3 does not make a difference. The reason there's only 2 on the right side is because these 2 carbons already have double bonds. So it's like a fully symmetrical molecule, okay? So you have a lot of symmetry here. You have that and that, right? So essentially, let me mark all the identical ones. Oranges are the same, right? I'm gonna mark them by their color, by different colors. So those 2 are the same. These 4 are the same. And then these are the same. How else can we look at this? First of all, just remember this. How many do we have? We have 3, right? We figured out there's 3. So I'll tell you, like, if that made no sense, this is what you can do. First of all, find all of the planes of symmetry and draw all of them in. Right now, we made 4 quadrants by bisecting with all of our planes of symmetry. Just choose one of those sections and mark every carbon that is within the section, including on the line. So I'm going to take this upper right quadrant. I'm going to mark this because it's on the line. I'm going to mark this because it's within. And I'm going to mark this. There's nothing here, right? So I got 3. And the thing that I just drew before, I showed exactly what everything is equal to. Like these 3 are marked in blue, but these are all different from each other, okay? So these are only unique types of carbons. So this will have 3 signals. This one, we have symmetry with these ethyls because they're all the same, right? Is ethyl, ethyl, and ethyl. So there's 6 carbons total, but there's only 2 unique ones, right? This is one, and that's another. So this will have 2. What about this? This does not have a plane of symmetry because this is a chlorine and this is a methyl. Therefore, every single one of our carbons on this benzene is different. So we have 1, 2, 3, 4, 5, 6. But we also have the methyl. So that's 7 signals. And then this one, we do have symmetry because these are both methyls. So let's do it, right? We can bisect it like that. That's the only plane of symmetry, because you cut it like this, it's not going to be the same, right? Only one side will have the metals. So we'll choose the top half of this, and we're going to count everything that's on the line if it's a carbon, as well as things in that half. So these are obviously not carbons, so we're going to count everything above it. So we got 1, 2, 3, and 4. We have 4 signals here. And lastly, I mean, this should be obvious, but this has like a bunch of, like, I don't need to be drawing all these, but I'm just doing it just to prove a point. I don't even know what else there is. It's like, so we'll choose one segment. We'll choose this segment. There's only one thing, which is that. But that was unnecessary, right? Like, it's just a benzene. It's all the same. There's nothing that makes any of the carbons different. So this one only has one NMR signal, right? So the most signals will be rank 5. So this one's rank 1, whatever, rank 5, rank 4, rank 3, rank 2, rank 1. Next one, we already talked about this one, ranked by energy of multiple bond stretch in the IR, and then I consider only the highest one. I mean, this is important, right? I feel like it's obvious, but some of these things have multiple of these multiple bonds, so just take the highest out of all of them and then use that to compare. So for this one, we have the benzene, which is really low. It's like 1600 compared to this, which would be higher, like 1740. So that's what it means. Just take the higher one. So this one is 1740-ish. This one is also 1740, but what's the difference here? This one has resonance with the benzene, so it's going to be less than 1740, right? Over here, the only multiple bond stretch thing will come from here, so that's going to be 1600. Over here to this, so the C double bond C is 1660. This might somewhat increase it, by the way, just saying. This is another one, but as you can see, it's in conjugation with this one, so it's going to be less than 1660. Okay, we'll just put like, I was going to say put greater than 1660, but it doesn't really matter. But anyways, now we can just use this to compare, and that's it, right? The furthest downfield is going to be 1, right? Don't forget, downfield is to the left, which is increasing values, right? Increasing. So that means that the greatest value will be rank 1. Okay, let's use this color. Anyways, rank 1 should be this one. Rank 2 should be this one. Rank 3, this is rank 5, rank 3, and rank 4. Next is asking about mass spec fragments, right? So let's just start like classifying the different fragments. This is secondary resonance, right? Secondary allylic. This is also secondary resonance. This one is just primary. This one is secondary resonance again. And then this one is secondary no resonance. So straight off the bat, right, it says the least abundant or the least stable fragment will be rank 5. So we can do that, right? This would be rank 5 and this would be rank 4 because those are just non-resonant. Now we're comparing 3 things that all have resonance. How do we figure this out? Now you look at the fragments, the radical fragments, right, and see their stability. So for this first one, it looks like we just cleaved off this thing right here, this methyl. So that's going to be a CH3. Okay, so this is a methyl. Let me just draw these radicals out first, and then I'll classify them. For this second one, what did we cleave off? We cleaved off this whole thing. So it looks like that. Okay, and then this third secondary resonance, which is the 4th molecule. What did we cleave off? We cleaved off this thing. So an ethyl, right? Now we can classify these. The CH3 is a methyl. This one is secondary, and this one is primary. Once again, radicals are like cations, so tertiary is better than secondary, is better than primary, is better than methyl. Methyl has nothing, right? So that means that the secondary one is our best, right? So this will be rank 1. rank 2, and rank 3. All right, the last one for now is rank by downfield shift in HNMR spectrum. So, I mean, this doesn't specify to look at the highest value, but it's implied, right, by this question, because this is asking for the downfield shift. So downfield, again, is furthest to the left, which is the higher side, right, the higher values. So let's take a look. It doesn't specify multiple bond stretch or whatever, if that even matters. Just look for the highest of all of these that has a hydrogen. So for this, it's going to be like this one, okay? In terms of the specific value, I mean, just look at your chart, right? For the aryl stuff, aryl, it just means benzene. So for the H's connected to the benzene, they're supposed to be around 7.2, but I will take note of this NO2 being there. That's probably going to increase it, as we saw in an earlier question. So I'm going to just straight up put like, you know what? I'm just going to put above 7.2. This next one, it would be this one again, right? Or, yeah, just like that or something, or one of these. So there's two things to note here. OCH3 is not, I mean, it's an electron donating group, meaning that they wouldn't have as strong effects as NO2. In this case, technically, because it can resonate with your benzene ring, it slightly actually decreases your expected value. So I'm going to put less than 7.2 here. Over here, it looks like we have an aldehyde. So aldehydes are one of your highest values. So this would be about 9 to 10. I'll just put a value of 9. Okay. Over here, we have a carboxylic acid. Carboxylic acids are the highest. It's between 10 to 12. So I'll just put 11. And lastly, we can just take a vinylic one, which is between 5 to 6. So I'll just say 5. Pretty simple stuff here. We can rank it based on our number. So the highest value will be 1, lowest will be 5. So the highest value is our carboxylic acid, making this 1, then 2, 3, 4, and 5. Okay. Now we can like do some more stuff. We can do some more practice, which I think is what everyone was looking for, just like NMR and IR stuff, this time combined. Now, there is no mass spec in this little section, but in the very last question, I promised there's some mass spec. But now we're getting used to doing like multiple molecules, right? So, I mean, not multiple different charts in tandem with each other. So this first one, C6H11BR1O2. Let's figure out the degrees of unsaturation. So it's 2 times 6 plus 2 minus 11 minus 1 over 2. That's 14 minus this 3. It's 1. 1 degree of unsaturation. Okay. So I'm just going to move this up here. 1 degree of unsaturation. And take a look at this. We have 6 carbons, but only 2 HNMR peaks. Or I guess we can say 11 hydrogens, but 2 HNMR peaks. I see a peak at 9H. That's kind of crazy. So 9H, we didn't go over this yet, but you might be able to infer that's probably going to be a tert butyl, because whatever else is going on over here doesn't matter. But these are all identical because they're branched, and each of those are at the end. So they all have 3 hydrogens. So 3 times 3 is 9. They're all identical once again. So they'd be on the same peak. So I am looking for something like that. So, I mean, I'll just go ahead and draw it in. Okay. Now I am looking for, let me just look at my IR because I need to see what my degree of unsaturation is. I have a stretch right here. It looks to be on the higher side. It looks like it's above 1700, so let's go like 1730-ish, okay? I could be wrong, right? 1740, 1730. So that's going to be a C double bond O. And that's going to be our degree of unsaturation, right? A C double bond O. Now, remember, as I was telling you before, this oxygen, there's 2 of them. The other oxygen can only be an ether or an alcohol, because it's not going to be a double bond because we already took that degree of unsaturation away. but we don't have any alcohol stretch over here, or acid stretch, which would look like that. And we also don't have any HNMR peak showing in OH. So it has to be an ether or part of an ester. And once again, I don't really see them giving you a ketone and an ether. Usually they just put it together. But if you're in doubt, you can always just test it out, right? Because I could be very, very wrong. But I'm just going with my first assumption, which is that it's probably an ester. Okay, so we're going to have an ester that looks like that. Now, let's see, what do we have? We have 6 carbons. We have, this is 4 carbons, this is 5, right? So there's going to be another carbon. So this is what I'm going to do, okay? This thing, it has to be, it's probably going to be, like, I don't know for sure, but I'm just saying, it might be connected like this, and then I have like a methyl with a bromine. Or I could maybe do this where I flip it. So I'm going to attach a methyl here, and then a bromine here, and then put my tert-butyl right there. I guess another thing that might come up maybe is this. So I just drew out a bunch of things. I didn't even look to confirm with my NMR and stuff yet. So I'm just drawing what the possibilities could be. Like, these are the only 3 things that make sense if I want to have an ester and a tert-butyl, right? These are the only things that make sense. So let's like look and see if these match up. First of all, I'm going to look at my NMR. So we already determined 9H is the tert-butyl thing. It doesn't say that it's a singlet, but it looks like a singlet, right? If they don't tell you, they'll at least make it look obvious. So it looks like a singlet, so it's a singlet, right? Now, what about this? We have 2H singlet. It looks like in all of these that the 2H is a singlet, right? So 2H, what the heck did I do here? Oh, never mind. 2H, right? They're all singlets. They're not near any other hydrogen, so they have to be singlets. So that doesn't really help me. But what I can look at is where this shift is located. So it looks like it's a little bit above 4. So if I look at my chart, right, it says that if you are next to 1x, okay, whether this x is oxygen or a halogen, then I'm going to be between 3 to 4. So that is going to cross out this one. The reason I'm saying this is because this peak right here, this peak would not be simply right above 4. Okay, because to get to the 4 value, all you got to do is be next to either an oxygen or a bromine. But if you're next to an oxygen and a bromine, that's some crazy deshielding that would occur. I would expect this to be minimum at 5, okay? Let's just say 4.9. I would expect it to be very, very, very off. This is barely above 4, and that's just the higher end of the range for being next to one of these X's. So I know it's not going to be this one, so I'm going to get rid of it. Okay, now I have to choose between the left and the right molecule. How am I going to do this? I don't even know. Give me a second to think. I got you. Okay. The first thing that comes to mind is from the IR. I mean, remember what I told you? Like, acid chlorides are very, like, they're very far downfield on the IR. And esters are also. So if you have both of them combined, I don't even know if this is like a real thing. I've never seen it before. Probably exists, but if this were to be real, it would be extra downfield. Like, I'm talking above 1800. This one, I'm just telling you, I know it doesn't look like it. I mean, it kind of does, but this is definitely not above 1800. So, I mean, that's like what I'm thinking right now. Nothing else. I don't really know. I mean, I might be missing something obvious, but that's like my biggest giveaway. So I know that the right molecule doesn't make sense. So the left molecule has to be right. Okay, next one. This one, first step, 2 times 4 plus 2 minus 8 over 2. This is going to give us 1 degree of unsaturation again. Okay, so we have 8 hydrogens, or I guess we look at carbons now because this is C-NMR. I guess, yeah, I forgot. I wanted to mention, I know you guys probably you forgot to label the charts. I did that on purpose. I didn't label any of these charts. I didn't say if they're IR, C-NMR, HNMR, because you should be able to tell. Just look at the scale and look at how it looks, right? So this is obviously C-NMR because it goes to 200, and the left thing is the IR, right? That's very obvious. Okay, so we have 4 carbons, but 2 C-NMR peaks, so symmetry. I see that we have a broad stretch right here, but it's not crossing 3000. So the broad stretch goes like this, right? So that means I have an alcohol minimum. What else do I see? I see, this is just typical sp3 CHs. Now, another thing I point out is this, okay? So I actually included this question in this video because somebody asked me about it, and I feel like the mistake they made is something you would make as well. So they saw this, right? And it looks to be between 15 and 2000, right? So they thought that this was a C double bond O stretch, but this is not. First of all, look at where it is. It looks to be about 16. I veered to the right. I mean, it's in the 16-ish area, right? So it looks to be like 1660, but that's not the main thing, right? Because you might argue like, okay, that could just be like a carbonyl, or like maybe I made it smaller on purpose. That could be an ester, I don't know. But look at the height of it. This is very weak. It just goes like this. Holy crap. It goes like this, right? This is a peak. It is a peak because look, these are not peaks, but this actually goes down. But if it was a C double bond O stretch, it would be like that, right? It would be very prominent. So 2 things tell me that it is a peak that's not C double bond O. One is that it's low, it's 1660, and the second one is that it's weak. So you know what that does match up to? It matches up to C double bond C. So I'm going to think that there's a C double bond C, and that makes sense because I do have 1 degree of unsaturation. But then the issue comes up, okay, what do I do with the other oxygen? I already made 1 in alcohol. The other one, like, can it be an alcohol, or like it can't be a double bond? Like, is it an ester, or, like an ether, or what is it? We don't have enough molecules to be able to do something like that and have a double bond. Like, I don't even know if I can draw what I'm trying to say. Like, let's say I wanted to do this. I have an alcohol. I guess you could do this. Yeah, I don't know. Something like that. You can do it, but you don't have symmetry. That's the problem, right? If you try to make like an ester and an alcohol. So what does that mean? That must mean that both oxygens are alcohols, okay? And we have an alkene, and we only have 4 carbons, so it should be pretty simple. I'm going to draw my double bond, and I'm going to just draw 2 alcohols. I'm missing 2 carbons. What do? Just place them one at a time on opposite sides. One over here, one over here. Now I'm going to confirm that this is correct. We have a bond stretch at 60, and if you look at your C-NMR, this is around the range of your alcohols, like carbon bond to alcohols. And there's only 1, right? There's only 1. So that makes sense that there has to be 2 alcohols, because how else would you have symmetry if there was only 1 alcohol, but there's only 1 bond corresponding to 2 carbons, right? So that's how we know that we have 2 alcohols. The second one is this. This is about 130. So if you look at your chart, it's about what's it called? This is going to be I think I'm stupid. Hold on. I need to take a look at my chart. I try to do it from memory, but I'm tripping. See, guys, not everyone is perfect. Okay. I knew I wasn't. Okay, wait, see, this is exactly. Oh my god, I can't even talk. This is an example of what I'm talking about. I'm just saying stuff, but whatever I said might not be entirely correct. I'm still confirming with my chart, right? So if I look at my chart, 130 seems to correspond to this thing right here. Okay, like a C double bond C. And this thing could be C double C bonded to alcohol, or it could just be like a regular alkyl that got deshielded. But it doesn't really matter because I have both of these going on. Like I have an alkyl that looks like I got deshielded. So that's good. You know what I'm saying? And I have. It's just weird because this is like a case where your C double bond C is also bonded to alcohol, and we have different stretches for both of these, but it works out, right? There's no other way I can draw this molecule. I think I'm going insane because I'm just making no sense. Maybe you can make more sense out of it than me, but it just makes sense to me. You know what I'm saying? I hope you know what I'm saying. But that's what we got. Okay, so we have this molecule. Now, same deal here. As far as if it's trans or cis, I don't want to feed you misinformation, so confirm with your professor because I've been hearing different things and now I don't even know what to say, but the structure of the molecule in general is the same, right? Whether it's cis or trans, and it matches up with all of our functional groups and our peaks. So this is how you would answer this question. Okay, now we're going to get into alcohol reactions. So as I mentioned before, like your alcohol reactions, a lot of them are similar or identical to stuff you did in OChem 1. So right now, like, you might remember from OChem 1 that mechanisms don't really matter much until the finals, and even then, like, they'll just ask you like one or two things and they'll be related to the newer reactions. So mechanisms are not too important for now, but I'm just gonna like breeze through these reactions just so you can remember them. I'll give you a couple tricks on some of them, how to remember exactly what they do, and I might run through a couple mechanisms just for your understanding, because just because you don't need to know the mechanism, like how to draw it, doesn't mean that you shouldn't even know what exactly is occurring. That's why I'm going to explain. So don't worry about memorizing how to write the mechanism. Just as long as you understand what's going on in the background, that's good. One last thing, I might skip a couple reactions because, as I mentioned last time in our exam review, the final exam review, it's your job to make sure you got all the reactions down. I told you exactly how to learn and memorize all the reactions. If you don't know what I'm talking about, watch the beginning of the final exam review video. So anyways, let's begin. Okay, I'm going to try to run this from memory. I hope it works. But the first one, I believe you start with oxidations, right? So let's talk about what oxidation is in general. Let's say you have an alcohol. You can oxidize it to an aldehyde, and you can oxidize it into a carboxylic acid. That is going to be for primary stuff, primary alcohols. If you have a secondary, the only thing it can be oxidized into is a ketone. And if you have a tertiary, this cannot be oxidized into anything, because oxidizing involves removing a bond so that you can add another bond to oxygen. The only thing that you can really remove is a hydrogen, but you can't just break off a carbon for fun. Like, you can't just break off this carbon and say, let me just replace it with another bond to the oxygen. That doesn't work. So that's what you should know about these. The funny thing is, I was going to mention this later, but the only time you'll see a difference between strong and mild oxidizing agents is with primary alcohols. So that's good. So let's start with strong oxidizing agents. These are going to be, KMNO4 is actually something that you learned last semester. So KMNO4 is a strong oxidizing agent. You also have stuff with chromium, so Na2Cr2O7. This Na can also be a K, right? They could write K2Cr2O7. There's also CrO3, or chromic acid. There's another one, NaOCl. So like all of these things with, oh, by the way, sometimes you'll see like this with H2SO4 or like H plus. Don't worry about all that. It's just like a workup thing. So these are the things, right? So H or KMNO4, Na2Cr2O7, CrO3, NaOCl. What I remember is if something has a chromium, it's probably going to be strong. Okay, KMNO4, it just looks like Cr for some reason. It just looks like CrO3. So I just think, okay, strong. NaOCl is a little odd one out, but has an oxygen. So I just feel like, okay, it's strong. I don't know, bro. But these are all strong. So what does that mean? The only difference you'll see between this and mild is with a primary alcohol. If you use a strong oxidizing agent, you're going to get a carboxylic acid. If you use a mild oxidizing agent, you would just get an aldehyde, right? So for these, if you react with the primary, you're going to get that. If you react with the secondary, you only get a ketone. And if you react with the tertiary, no reaction, or you can just say you have the same molecule. Okay, so that's strong. Now let's do mild oxidizing agents. So we have PCC. I think there's like PDC. There's also like DMSO, which you might remember as a solvent, polar aprotic solvent. DMF, dimethylformamide. If you're wondering what these look like, that's DMF. DMSO is that. PCC and PDC, I don't feel like drawing. But anyways, what I want to tell you, there's a couple of things. As you might be able to infer from this, strong oxidizing agents use actual elements and like you have an actual compound. It looks like the mild ones are just acronyms. Like this stands for pyridinium chlorochromate, dimethyl sulfoxide, dimethylformamide. These all stand for something. So these have stuff going on that causes them to be mild. That's how I remember. They're all acronyms and they're mild. Another thing, PCC in particular, you know how I remember it? Remember this for your MCAT, if you're taking MCAT. Please create carbonyl. Okay, let's go back to the original definition of carbonyl. A carbonyl is an aldehyde or a ketone only. So PCC being please create carbonyl means it will only create a carbonyl, which means if you have a primary alcohol and you react it with the please create carbonyl, you're only going to create a carbonyl. You are not going to do this. You're only going to create the carbonyl. Okay, I hope you remember that. Some little fun way to remember that. But the simple thing is that all the things with acronyms are going to be they're going to be the mild ones. And if you're wondering, how do I know if this is an acronym or if it's a formula? I mean, do any of these look like formulas? Like P is phosphorus, right? But why would it be CC? It would be PC2 if it was a real thing. And then like, are you serious? Like D is not an element. It's an isotope of H. And then like, what is M? So these are all acronyms. Just know that they're going to be mild. For the 15th time, the only difference between mild and strong that you'll really see comes up in primary alcohols. The mild will end here and the strong will end over here. They always teach you that you react like an alcohol with a mild or strong oxidizing agent, but don't forget you can also just react an aldehyde. Like you can react an aldehyde with a strong oxidizing agent. If you wanted to make into a carboxylic acid, that's perfectly fine, right? If it's not fully oxidized and it can be oxidized more, then you can react that thing with a strong oxidizing agent. So that's it, right? That's it for these strong and mild oxidizing agents. Now there is one more like category I guess you could include. It's gonna be like the selective, right? Selective oxidizers. So when we talked about like strong and mild, like PCC and then NaOCl, right? This is mild and this is strong. They just try to oxidize it, whatever, right? Like primary and what the heck, secondary. Okay, and I mean they can oxidize something that's secondary allylic and secondary or primary allylic, right? They can do whatever. However, if you just wanted to oxidize something that's allylic or benzylic, then you're going to use something called MnO2. So this is selective for benzylic and allylic primary and secondary. Now, this one is weird because KMnO4 is strong, but this is actually mild. So this is like a little odd one out. Selective and it's mild. Doesn't have that brute force capacity to fully oxidize. So it's going to be mild. So to give you an example, if you have let's draw that. Okay, if you wanted to run this with the MnO2, for fun, let's put a wedge. What is this going to do? Is it going to cause this to happen? Right? So this is how I look at it. The carbon that the oxygen is on is next to the benzene. So it's away, like one away from the, or I guess just right next to the benzene or double bond. That makes the oxygen like the allylic oxygen, which is what MnO2 is selected for. So it's going to cause this to become a ketone, whereas this just stays as an alcohol, even though it's an alcohol, right? It's a primary alcohol. Another example, let's do this. We're running it with MnO2. Let's see what are viable options here. This one works because the carbon is allylic to this double bond. This one has nothing, so that's not going to be touched. And this one also works because its carbon is one away from the double bond. So when we redraw this molecule, we draw the product. This alcohol remains untouched. This one will become oxidized into a ketone. And now this one, it's primary, but it only becomes an aldehyde. It does not become a carboxylic acid. So this is what your final product would look like for these MnO2 reactions, the selective stuff. Okay. So that's it. Now let's talk about tosylation, which we all should know from OChem 1. So tosylation, TSCl, right? So this is what tosyl, let me just draw better. This is what tosyl chloride looks like. And its purpose is to make alcohol a good leaving group. So alcohols are horrible leaving groups. I don't think I have to explain why. But if you want to make it a leaving group, you're going to react it with TSCl and turn it into a tosylate. Now, please don't forget, you don't invert stereochemistry, okay? Because what is happening, this tosyl, like this oxygen is being bonded to the sulfur and the chlorine's removed and whatever. Inversion of stereochemistry only happens if you're doing something to the carbon that you're on. But that's not being affected. The oxygen that's on the carbon is doing its own thing. So the carbon is untouched. That means that no matter what happens to this thing, you're going to be on a wedge. So it would look like this right here. pH meaning benzene. Okay, so this is tosylation. Now you can do stuff, right? Like you can react with it, like it's a leaving group. So if you just use like a nucleophile, you can attack that, kick this off, and you get that, right? I don't know what else they want you to know about this. But don't forget tosylation. Okay, next. Oh, I guess once again, why is tosylation good? I mean, you should already know this, right? But once the oxygen leaves, it's going to be negative, right? And you have resonance, so that's why it's good. Okay, next we're going to do reduction reactions. So I think, yeah, whatever, let's do it. So we talked about oxidation. We talked about how to go from here to like that or something. How can you go backwards? That's where reduction comes in. So we have NaBH4, LaH, and I think that's all you need to know, like H2PT. I think that's all you need to know. So anyways, NaBH4 can only reduce acid chlorides, aldehydes, and ketones. LaH can reduce everything NaBH4 does, plus other things, right? So you got your other carboxylic acid derivatives like esters, dioesters, etc. So that's LaH. Now H2PT specifically is just going to reduce double bonds, right? This is not H2 rainy nickel. This is just H2PT. So if you wanted to reduce something like, I don't know, like an alcohol or something, you'd have to make into a double bond, which is where my next thing will come in. Let's say you have this, and you want to make it into that. How would you do this? The first thing you do, you can use LaH or NaBH4, doesn't matter. Make it into an alcohol, and then use H2SO4, which does dehydration, which makes a double bond. And then you can use H2PT or nickel, and that would make it into just a cycloalkane. Not much to it, to be honest. I guess one more thing you can remember is that this causes like a syn addition of your H's, but I don't think that stuff really matters. That was more of a focus for OChem 1. All right. Next. Another new type of reaction is it's called PBr3, phosphorus tribromide, and there's also SOCl2. So the way this shows up is they'll give you something like this. And they'll say you're reacting with PBr3, and the ultimate product looks like that. If you were reacting with SOCl2, you would get the chlorine counterpart of that. So essentially, you're replacing the OH with a bromine or a chlorine, depending on the reagent, and you're inverting stereochemistry, which is indicative of an SN2 type reaction occurring. So, I mean, that's kind of all you need to know about this. I guess, like, I'll tell you why this occurs very briefly. So it's kind of like, okay, we obviously know OH is a bad leaving group. So the reagent PBr3 will both stabilize oxygen and have the bromine attack it to give you this molecule. That might not have made any sense, so I'll just go ahead and show you. So PBr3 is like a Lewis acid, right? And the oxygen is a Lewis base. And so the oxygen will bond to the phosphorus, but the phosphorus needs to break a bond. So it's going to break off one of the bromines. And you're going to have this now, right? So you're bonded to the phosphorus. And what did I say? You had a bromine that got kicked off. So this structure, once it leaves, it's stable because it's just stable, okay? It's stable, and now the bromine can attack it because this is like a good electrophilic carbon because it has a good leaving group. that wants to leave. So the bromine will attack it like from the back, right? Backside attack. And you ultimately end up with the inverted alkyl bromide. The same thing is for SOCl2. SOCl2 just looks like that. But it's like the same concept. Your oxygen will attack the sulfur and then kick off a chlorine, and then it's stable because I said so, and then the chlorine will attack, right? So you don't really have to know the mechanism. I'm just explaining why this type of thing occurs, but definitely something new and is good to keep in mind, right? It's a good reaction. And you're going to see like SOCl2 again in a different context later on, but also now, like in a little bit. So just remember those reagents. I believe there's also like a reagent called Pi2, which does the same thing, but as iodine. So if that's in your notes, keep that in mind. And, you know, because it does SN2, you typically would not, you typically wouldn't react this with PBr3 or SOCl2. If you wanted to do this, if you wanted to replace the OH with the bromine, you can just do HBr, right? This is like an old reaction. And I think they do reintroduce it anyways. If you wanted to go from that to the chlorine counterpart, instead of SOCl2, just do HCl. Because this is tertiary, which is hindered. It's too hindered for SN2. So if you have a tertiary, I would just do HBr, HCl. If you have primary, secondary, obviously like an unhindered secondary, then do SOCl2 and PBr3. Okay, moving on. So next we can talk about something you don't really have to know the name. It's called a Williamson ether synthesis. Just give me the name in case you want to look it up in your notes, but it's actually just an SN2 in disguise. I mean, it's not really in disguise when you look at it, but the name makes you think it's something else. But let's not forget an ether is this, right? Just an oxygen in between two carbons. So the way this works is you have an alkyl halide, and then you react it with some oxygen nucleophile. This is pure SN2 right here, right? You attack the carbon, and you kick off the bromine, and you get the oxygen is attached to this, right? Now it's an ether. That's all this reaction is about. I guess something I want to mention that you also still should know from OChem 1, but you might have forgotten, is that you can make an alcohol into a nucleophile. So usually you use NaH, but any strong base is acceptable. But NaH is a big one. People mistake it with NaOH and they get confused. I mean, both of them are strong bases, but this is like the strong base, right? So NaH, in reality, it's a H minus, right? That's what Na is, just a counter ion. So it's an H minus, and it's going to deprotonate the oxygen so that the H just becomes H2. It's normal, right? So that's going to make an O minus, and then you can attack whatever alkyl halide you want, like that, right? And get your desired product. So this is an instance of SN2 coming up again, but it's mentioned in your notes. So also, you know, SN2 is fundamental. It should not be difficult. Should not be scary. It's very chill. Okay, a new-ish type of reaction. It's like based off an old reaction, but it looks a little different. It's called like a pinnacle rearrangement. Doctor handwriting. Can't apologize for that. If you have a molecule that has a vicinal diol, okay? Vicinal diol means they're 1, 2 to each other. So this is not a vicinal diol because this is carbon 1 and carbon 2, right? The oxygen, they're 1, 3 to each other. So that's not vicinal. Vicinal means they're like right next to each other, like on adjacent carbons. If you have a vicinal diol and you react it with H2SO4 and I guess heat, then you're going to get a product that looks like this. I mean, for this specific reaction, the way it works is, first, what do we know H2SO4 is? It's a strong acid, right? So the strong acid is going to protonate this, and you're going to have that, and it's just going to leave, right? It's going to leave to give you a carbocation intermediate that looks like this. Now, what is going to happen here? Your methyl is going to shift over there because it is tertiary, but look what happens when you do a rearrangement. You have a allylic, right? I mean, this is secondary allylic to the oxygen, and the oxygen will do something like that. And then it just loses a proton because of the HSO4 minus. I'm zooming through this on purpose just because you don't really need I mean, yeah, you don't really need to know it. But this is what you get, right? You get this product. That's how it all worked, right? It's just about carbocation, stabilizing it, and satisfying charges and whatever. So as you can see, both of these sides started with 2 methyls. You had 1, 2, and 1, 2. And ultimately, and they both had alcohols, right? Ultimately, one side gets the 3rd methyl, and the other one becomes a ketone. Let's say you had let's say you had that. Basically, the same thing would occur except you don't have methyls to give. But what can you do rearrangements with other than a methyl? You can do it with a hydrogen. So, I mean, you can just think of it like this, right? The same thing is going to occur. And one side is going to become a ketone. The other one will just have 2 H's instead of 1. So, like, that's what it would look like. So that's how this reaction works. For the same reasons. Okay, let's do another reaction. Let's actually, okay, we're gonna make a vicinal diol now. So if you have this, right, this is a repeat of a reaction from the past. So you might remember osmium tetroxide. If you have osmium tetroxide, and I guess sometimes they add peroxide, this is going to give you vicinal diols. And technically, these are syn to each other, syn addition. I don't recall having to remember this stuff. Yeah, it's not as important as it was for the OChem 1. So I'm not going to focus on that. But you're doing a syn addition of diols. And the reason I brought this up is because you can set yourself up to do the pinnacle rearrangement. So H2SO4, and then you can get that. Okay. Another type of reaction would be, it was going to be a new one. It's like related to this, but I'm just going to erase this and then bring it up again. So this one I really want you to know. All right, new reagent. Guys, this does not say periodic acid. This is not periodic acid. It's periodic acid because what's it called? Iodate, and then this is the iodate ion. This is periodate. If you remember from Gen Chem how this stuff works. Anyways, this is periodic acid. This is a very important one for this chapter because as you might remember in OChem 1, I really emphasized knowing reactions that break carbon-carbon bonds and build carbon-carbon bonds. This is like, I think, the only one in this exam that breaks carbon-carbon bonds. So this big asterisk, right? This is going to break carbon-carbon bonds, but specifically if you have a if you have a geminal diol, okay? What am I saying, man? Vicinal diol. Vicinal diol meaning they're on adjacent carbons. So we don't have to get into details of what goes on in the mechanism, but ultimately you're going to just cleave it and you're going to get this. So if you want to see what happened, the way to approach it is, first of all, make sure that your carbons with oxygens are adjacent to each other. And you just cleave in the middle, right? Cleave it, pull to the sides, and oxidize, okay? So we pulled that thing to the side. What do we have? We have that, and we have that. And just oxidize. So this obviously can take one more bond, right? It's missing a bond, missing a bond. So oxidize it, make a ketone there, make a ketone there. You guys might remember like this thing, right? When we did oxidative cleavage in OChem 1, this is what we did. We just cleaved the double bond, pulled to the side, and then did whatever we needed to, right? So this is just like that, except it looks slightly different because you're going to have alcohols attached this time. But that's all you're doing. Let's do another example, because I need to tell you something, right? Low key, I'm going to do this. Okay, so I have some long molecule. Okay, I see that we have this going on. So I'm going to locate that and I'm going to cleave it right here. Pull to the right, pull to the left. Now, what do I do here? Do I make an aldehyde or do I go all the way to carboxylic acid? What about the other one? Do I make it into a formaldehyde or do I make it into CO2? So periodic acid is going to do mild oxidative cleavage. Okay, so you're going to cleave it, but you're going to just make a carbonyl. Please create carbonyl. So this is what you would get for one side, and then the other side would just be this formaldehyde. We'll do one more example. Okay, I see this reacting with periodic acid, cleave it, and pull to the up and whatever, left and right. So now we're going to open this up. So we got this made into an aldehyde and that one made into an aldehyde. Okay, this is perfectly acceptable too. You don't have to open up the whole thing, or I guess you can't even do it because it's still a ring structure. But, you know, keep it in its same conformation if you need to, if it makes life easier. That's perfectly fine. So one more time, you're just going to make aldehydes. You're not going to oxidize it further. However, what if I wanted to go from that to a carboxylic acid? You better be thinking the correct answer in your mind. There is no reagent they taught you for this. So what can you do? Step 1 is make this. Step 2 is react with a strong oxidizing agent. Remember what I said, right? They teach you how to go from alcohols to carboxylic acids and whatever. And they never emphasize going from a carbonyl to a carboxylic acid, but you can very well do that if it has space for it. So all you got to do is react with a strong oxidizing agent. We'll use CrO3. CrO3 is going to give you this. It's going to oxidize the aldehydes further because they have space. They're going to become carboxylic acids. So definitely make that connection. One small thing I want to mention, it showed up in PLTL, but I don't know if it is really taught in class. But we talked about how, in general, Na2Cr2O7 and stuff like that are strong. If you were to react this and you have something called pyridine, if that's like your solvent, the pyridine will poison it. And as a result, you're not going to be able to fully oxidize. So you would get an aldehyde, even though you have a strong oxidizing agent. The way I remember this is pyridine, right? PCC stands for pyridinium chlorochromate. So the P is this thing. If something has pyridine or pyridinium, it's probably going to be weak. But as far as you're aware, PCC stands for please create carbonyl. Okay, we're almost done. There's a couple more reactions. One very, very fun. Well, it's fun to me, but it's like a very useful reaction. It's like related to biology too, and you'll see it on your MCAT, so that's fun. It's called a Fischer esterification. Right, so basically, this is what it looks like. You're going to have a carboxylic acid plus some alcohol, and you react it under acidic conditions, and your product looks like that. Now, I will go over the mechanism just for the curious people, but you do not need to know it. The very easy shortcut is to take a look at this, right? You keep your carboxylic acid the same, okay? And all you're going to do is replace the hydrogen with the R group from this alcohol. So you see what I did? This R group is an ethyl. So I just replace this hydrogen with an ethyl, and that's my product, right? If I give you another example, let's do this with H plus. Simple, okay? Draw this exactly the same. Forget the hydrogen. So we're going to draw exactly the same. Keep the oxygen. And we're just going to take this and attach it. So we're going to draw exactly as it is. And that's my product. Now, in reality, this is called a dehydration synthesis reaction. So you're synthesizing two things by dehydrating it or removing a water molecule. Now, which ones are being removed, like which O's and H's are being removed? It's actually this and this, right? Those two are being removed, or whatever, those three molecules or atoms are being removed. These are leaving as water, and you're bringing this into there. That's what's like really occurring. So now I'm going to run through the mechanism for the tryhards, but I'm actually going to do like a simplified version of it because the official mechanism is it's just too much for new people to keep track of, so we'll just do some shortcuts. So let's say we have this, and we're reacting with that. You're in acidic conditions, right? You have to be in acidic conditions. So what we're going to do is we're going to protonate this oxygen. So that's going to become OH plus, and then you bond it to OH, right? Now, this oxygen is going to attack this carbon to kick that bond up, right? So we can relieve all charges. And this is going to give us that plus the thing that we just added on, which is now positive. Now, something called a proton shift or a proton transfer will occur. Essentially, this one wants to lose its charge, and we're ultimately trying to get rid of this one. So the H will shift from there to there, right? That's what's happening with the proton shift, and you'll get this. Okay. Now, this is a leaving group we're trying to get rid of. So this oxygen will come down, reform a double bond, and kick this water off. And you're going to get this OH plus again, plus that. And so the water molecule is gone. And ultimately, we just have to get rid of this positive charge. So you're going to lose a proton through workup or whatever is involved. And you end up with that ester. So that's what's actually occurring. And once again, this is the simplified mechanism. But as you can see, the OH that was on the original carboxylic acid plus a hydrogen from here, that is going to be the water molecule that ultimately leaves. While this, while this plus this combine. So that's Fischer esterification. Now, lastly, we have, it's like two things together. Okay, so you can do the same thing. You can do a Fischer esterification, but with acid chlorides. So like, if you have this and you reacted with an alcohol, you'll get the same type of product, right? So your product will just look like this. Attach this whole thing on, that's your product. Now, how do you make an acid chloride? As of right now, there's only one method which is going to be carboxylic acid reacting with SOCl2. So SOCl2 shows up again. That's going to give you your carboxylic acid. We don't need to get into the mechanism. Just know that your OH will be directly replaced with the Cl, even in this carboxylic acid. So, you can go obviously from this to an ester, but if you're being weird, you can make an acid chloride and then go to the ester. You know what I'm saying? But yeah, that's pretty much it for the reactions. There's probably some other stuff that I forgot, or there's some like minor things. Definitely take a look back at your notes just to see if I miss anything and familiarize yourself with those. One more time, the mechanisms are not too big of a deal for now. As long as you have like a general idea of how to deal with reactions, even if they show up a little differently, that's all that matters. Okay, now let's get back into what we actually care about, which is how do we figure out questions with IR, NMR, mass spec, etc. So this is a question from an exam 3 years ago, and last year's exam also had something like this. I think mine also had something like this. It's just, they just word it slightly differently, but the essence of the question is the same, where they give you a reaction map like this, and they want you to figure out step by step what molecules or reagents you have. I left this towards the very end because now we can include the reagents part. So a quick little tip I'll tell you is that because of how limited the reactions are in this unit, that can like be like a very simple giveaway. I don't know how to explain that. No, I know how to explain it. I got you. So like, for example, if you make a molecule with an alcohol. Nah, that's a horrible example. Hold up. Okay, if you make a molecule with like a double bond, the only reaction that you do anything to a double bond with in this unit would be like H2PT. Like for the there might be one more that I missed, but you can just use your little word bank in your mind of reactions that that do stuff to things like this, right? So you can think like, okay, that's the only thing I can possibly do. So molecule B must be like a product of reacting with something like H2PT. Honestly, let's just do alcohol, right? Or let's just do carboxylic acid. if I have a carboxylic acid, there's not that many reactions in this chapter that involve reacting with the carboxylic acid specifically. If it was just like an alcohol, sure, I get it. But carboxylic acid is not an alcohol. And they only taught you like one, unless I'm being stupid again. But the one that I'm thinking of right now is the SOCl2. So if molecule A has a carboxylic acid, you can think, I might be using SOCl2 in reagent 1. Worst comes to worst, just throw something random. Let's just say you don't know anything, just throw something random that was in your chapter, and hopefully you'll get it right. I actually did that on my exam. I think I didn't know. Yeah, I think I got molecule A, but I didn't know what molecule B was, which I just put some random thing and I got it wrong. But then reagent 1, I just guessed out of the possible options that could have reacted with something from molecule A, and I actually got it right. So that was pretty good. So what we're going to do is, let's just read the question real quick, right? It says that we have a molecule with C9H12O3, and they give us all these different charts. Okay, cool. So first step, as always, is to find the degrees of unsaturation. So 2 times 9 plus 2 plus minus 12 over 2. This is 8 over 2, which is equal to 4. Now, okay, so we have 4 degrees of unsaturation. I'm just going to assume that there's a benzene because that makes our life much easier. If that is not the case, we're honestly really cooked, but I'm going to draw a benzene. So we have a benzene. Now we got to figure out 3 oxygens. That would be crazy, right? If none of those are contributing to the degrees of unsaturation, they're all going to be alcohols or ethers or a mix of that. So there's just something to keep in mind, not that big of a deal. If we look at our CHEM, we can see that we do have some aromatic peaks right here. And it looks like there's only 4. Okay, so there's 6 H's in a benzene, but only 4 of those are actually free, right? So 2 of these carbons will have substituents on them. So that's one thing I'm going to keep in mind. 2 subs on benzene. Okay. It also looks like 2 are identical and another 2 are identical within those 4. So there has to be symmetry, meaning that I'll have a benzene that has a substituent like that and a substituent like that are like opposite from each other, 180 degrees. Because if A and B are different substituents, this is the only way I can maintain symmetry, right? This would be identical to that, and this would be identical to that. So that's something else I'm going to keep in mind. Okay, what else? We have... Oh, I forgot we have all this other stuff. Okay, great. We have an IR chart of A, and I see this right here. That's an alcohol peak, right? Specifically in alcohol, not a carboxylic acid, which is good because we shouldn't have a carboxylic acid. We don't want another degree of unsaturation. So I'm probably going to have an alcohol. Okay, I'll just draw that. What else do we got? Between 3 and 5, we have all these other peaks. So that, they are not like they're not at the alkyl range. They could be alkyl, but just like connected to stuff. And I'm being vague on purpose because I want you to figure it out. But hopefully you thought exactly what I'm thinking, which is that you must be connected to oxygens in the form of an ether or, once again, an alcohol, right? Because that's going to put you in the 3 to 4 range. And I see something at 5. So the fact that I have 3 oxygens means that I might be close to like 2 oxygens, right? If I'm close to 1 oxygen, I'll just be 3 to 4. If I'm close to 2, I might be even higher than that, right? So that's good to know. So I'm gonna just start drawing some stuff. I guess like what we got 9 carbons and we use 6 of them. So I'm gonna draw something right here and something right there, right? For sure it's gonna be like that. The other 3, I'm sorry guys, this right here is in alcohol and it's a singlet and it makes sense. This is an alcohol that That's why I was being stupid. Alcohols are 2 to 5, right? Don't forget. But this one makes sense to be the alcohol because, first of all, we know that we have an alcohol from this. And this one has to be an alcohol because it's a singlet and it's 1H, right? We have a singlet right here, but that's 3 H's, so that doesn't make sense. So this is going to be our alcohol. Okay, so I see this right here, right? My other 3 carbons are not going to have symmetry because 2, 3, and 2 does not indicate symmetry. Those are coming from 3 different carbons. Like, what does this mean? The 2H is coming from a CH2, this is coming from a CH2, and then that's coming from a CH3, right? So there's no symmetry here. So that's something to keep in mind. I'm just going to go ahead and just draw. I'm going to draw like an alcohol here and here. Let's draw 1, 2, something like that, right? So here's the thing. I just attempted this. First of all, I think I'm missing a whole carbon. So yeah, that's cooked. Hold up. Here, we can do that. Okay, we can start with this. Let's see if this even works. So like, I have, let's take a look at this. This is going to be CH2. And if I look at my chart, let me erase. I know this is not correct because I don't have a CH2 that's a singlet, right? This is between 2 oxygens, so there's no adjacent hydrogen available. So I did something wrong, right? So I can like pay attention again to these multiplicities of, here, let me just highlight them so you know what I'm looking at. Come on, man. Okay, so I'm looking at these. So I'll just go ahead and start with this, right? This is obvious. This is a CH3 and it's a singlet. So the fact that it's a singlet means that it must be like away from an oxygen, or what am I saying? Away from other carbons, meaning an oxygen must be there. So something like this makes sense, right? Where it's an OCH3. OCH3 makes sense for that. But what about these two, the 2 HTs? These two must be next to each other. It must be something like this. You see these two? These are both CH2s. And considering that they're not identical and that these are not carbons with H's, these would both show up as peaks that are 2H and N+1, which is 2 plus 1, which is triplets. So I want to make sure that they're together. So we're gonna go ahead and redraw this. So this time I'm just gonna draw like an oxygen here, and I'm gonna put 1, 2, and then oxygen, CH3. Okay, so this looks like a valid answer because now, same thing, we still have a 3H singlet over here. These two are both going to be 2H triplets and they're not identical. So we're going to have 2 different 2H triplet peaks. So that's good. Now, as for the specific values, that's where something looks a little bit off, but I don't really care because if it works, right? But what am I saying is off? It looks like the left one is further downfield than the right one, even though they're both very similar in the sense that they're both like between 2 oxygens, same distance. Now, the reason why one of them is more deshielded than the other could also be the proximity to the benzene, the phenol. So I don't really care too much. I think this looks like a valid answer. So I'm going to pursue this, okay? We'll say this is reagent A. Now, reagent, this is molecule A. So just call this A. Okay, I was going to like keep myself quiet, but I'm telling you right now, I did something wrong. But I'm not going to tell you yet. I'm going to tell you later because right now I'm acting like a student who's just testing stuff out. and finding out their issues later. Okay, so that's A. Right off the bat though, I guess we can just address it. As I mentioned, they're gonna ask you for a reagent, and the reagent will be something that you just learned, like for this exam. And I don't really see like how I can do anything to this molecule, especially because this is an alcohol reaction chapter, right? And I do have an alcohol, but it's on the benzene. And although we are in OChem 2, you don't touch the benzene until exam 2, because you just haven't learned anything that alters a benzene. So like if I were to do an SN2 reaction, I would have to attack this carbon, and that's a benzene carbon, which I can't do. So right off the bat, I'm thinking I did something wrong, even though all of my peaks and my stuff are adding up. But we can address it right now, or we can come back to it later. But I think we'll just go ahead and fix it right now. I see that one way I can maintain all of my peaks and all of my splitting and all of that stuff is by simply swapping this with that. So I'm going to do it, and I'll just draw it over here. Okay, so I'm going to put my OCH3 over here, and I'm going to put my other substituent right here. So as you can see, I still have a 3H singlet. I still have my 2H triplet, and then my OH singlet. And then obviously these two are the same, and these two are the same. So I have all of my peaks, all of my splitting, all that stuff is good. And now if I were to do some sort of SN1 or SN2 or whatever type of reaction, I can easily touch this carbon because it's just a regular sp3 carbon. So now this looks like a better answer. So right, once again, although these two are similar in their C-NMR, H-NMR, I mean, obviously there's a difference, right? They're not going to show up identical, but you might not necessarily know what the exact difference is by just looking at one NMR. If you're given both of their NMRs side by side, maybe you can argue which one is correct for one compared to the other. But if you're just given one, you're not really sure if something is affecting something as much as you expect, right? Like, remember I said this might be being affected by this thing. It could also be that this is being affected by the fact that there's an OH compared to like an OCH3, right? There's so many different like factors that could affect both of these molecules that are very similar that I don't really know if I can figure that out. So I'm going to use another clue, which once again is this, the reagent 1. I know that if this was the right molecule, I would be screwed because I can't do anything with this alcohol. So that means that this should be the correct molecule because I can actually do something with this alcohol. Okay, so let's look at B. So B, they gave us an IR and a mass spec. I'm going to skip to the mass spec because I feel like it. So the mass of... hold up. Okay, I was going to look at the mass of B, but it's not provided. We just have mass of A. That's fine. I guess one thing I'll point out is starting with the IR. There's no stretch for the OH, so that's gone, okay? That's literally proof that I'm doing an alcohol reaction, right? Forget my whole theory and whatever I was talking about. This is proof that we did an alcohol reaction because we had an alcohol to begin with and now it's gone. This is how organic chemists understand what reactions are occurring, by looking at these graphs and seeing how different functional groups appear or disappear. Okay, so we did an alcohol reaction. I'm automatically thinking about the different ones that I could have done, but whatever, let's see. I see... Guys, I'm like stupid, bro. I made this mass spec and I did the mass wrong. Okay, I'll just point it out to you. I was trying to make this the M plus peak, but that doesn't make any sense because this molecule has a different mass now, but pretend it's the M plus peak, okay? Forget everything else. The thing that we're looking at is that we have an M plus peak at 168 and we have an M plus 2 peak at 170. That means that we must have a halogen present. The M plus and the M plus 2 peak are 1-to-1 ratios, which means that we have a bromine. So once again, this mass is wrong, but just ignore it, okay? You get the idea. So it looks like we added a bromine in place of the OH. Now, we don't have like HNMR or CNMR data to tell if we added like another carbon or another benzene or whatever, but this is where knowing your reactions comes in. We're using one single reagent. The only reagent that we know attaches a bromine in place of the OH will do only that, right? What am I saying? If I wanted to replace the OH with a bromine, I would have to use either HBr or PBr3. I'll tell you which is the right one, but give me a second. You have to do one of these, and no matter which one you do, all it's going to do is replace the OH with a bromine. So you're not going to be able to add like a carbon or a benzene or anything else here. So because of that, you don't have to worry about there potentially being another functional group added somewhere in this molecule that you can't see because they didn't give you the C-NMR or whatever for it, because it's not possible by what you know. Okay, so PBr3 is the preferred one. HBr is going to be used for tertiary. Technically, it's fine. You just don't want any unwanted rearrangements, but I would just use the new one. PBr3 will prevent any of that side reactions. So PBr3 is going to be reagent A. So I'm just going to go ahead and write it right here. So that's PBr3. This is molecule A in green. Okay, cool. So that's our molecule B, right? We got our benzene, methoxy. Okay, this is molecule B, and everything looks fine. Let's move on. Okay, reagent, what's it called? C. Let's look at C. One thing that stretches out, one thing that stands out to me is this stretch right here. Now, is this a secondary amine or is it a terminal alkyne? Our proof is right here. We have a stretch at 2200-ish, which is C triple bond C. So that means that this stretch right here has to be C triple bond C hydrogen, right? The sp hydrogen. Now, if you were confused, let's say you completely forgot about this and you just didn't know, is it NH or is it SpCH? What I will tell you is there any reaction that you know right now that can just attach an amine to a molecule or even replace a bromine with an amine? Like you don't really, I mean, I guess you could do like an SN2, but it's very unlikely. It's not like a new reaction, right? So it's probably not going to be an amine. So, I mean, obviously we just proved it that it's not an amine. It's a alkyne, terminal alkyne. We have a terminal alkyne. Now, I don't really feel like looking at my C-NMR because I just can't imagine a bunch of stuff going on. Because same exact thing. I'm just thinking, okay, I have an alkyne and I had a bromine, right? Let me actually draw molecule B again so I can tell you my thought process. Okay, so I'm supposedly adding in alkyne somewhere. How would I do that? Like, you know, the only thing I can think is that you make an alkyne nucleophile. You might be thinking that you can turn something like this into an alkyne. That's only possible if you have two halogens, either on the same carbon or vicinal to each other. And then you do, I think it was like NaNH2 or KOH. So that's if you have two, but we only have one. So the only way I can somehow add or replace something or whatever with an alkyne is through an SN2. That's why I don't really care for the C-NMR much, because I know there's, you know, nothing else I can do. I'll probably just use the C-NMR to prove that my answer is correct, but as of right now, I'm gonna just pursue what I'm thinking. So I know that it has to be a 2-carbon alkyne, because if I were to do something like this, like 3 carbons, and I attacked that, look at what my product would be. Would I have a hydrogen that can show up over here? No, right? So that means it has to be a 2-carbon alkyne, because one side will be deprotonated to be the nucleophile, and the other side will have the hydrogen that shows up on our peak in the IR. Okay, so this is what I have. Let's just confirm it with our C-NMR. Our C-NMR has 1, 2, 3, 4, 5, 6, 7, 8, 9 peaks. And my molecule has 1, 2, 3, 4, 5, 6, 7. Am I stupid? Oh, oh my God. I got so scared for a second. Oh my God. Okay, whatever. This is 1 carbon. This is 2 carbons. 3, 4, 5, 6, and 7. But we also have this one, 8 and 9, right? I'm actually so stupid. So we have 9. Let me just do that again because I made that confusing. So these two are identical. That's 1 set of carbons. 2 set of carbons. 3, 4, 5, 6, 7, 8, 9. Okay? We have 9 carbons, so we should have 9 peaks, and we did have 9 peaks, right? You can confirm if they're in the right position or not. I don't really care because I know they're correct, but that's what it is, okay? So ultimately, molecule A was this thing right here. Reagent A was this. Molecule B was this thing. Reagent 2, I'll just draw it over here. Reagent 2 was this, or you can just write it as Na or Li. And molecule C, it was this thing, but let's draw it nice and clean. It was that. Okay, so now that we're all done, I just want to mention one more random thing that I remembered right now. There's probably a billion more things that I forgot. And if there is something that I forgot that I remember after posting this, just check the comment section of the video and I probably would have mentioned it there. But I want to go back to IR for a second. We talked about, OH having like a broad stretch, right? Like that. So let's say that you have 3,000 and 4,000, right? And you have like a peak that is broad, but then has like a little point and it looks like that. Now, this is not a carboxylic acid stretch just because it's not going down to 2,500, but it still looks weird. We have like a little thing here. The thing that causes this is overlapping of peaks, right? There are many things that can be up above 3,000, right? We talked about the alkyne hydrogens and amines, right? So if you see something like this, it very well could be an overlap of peaks. So the broad part of it will tell you that you probably have an alcohol. And this thing could tell you that's either an amine or an sp hydrogen. So obviously, depending on what other peaks you have, you can determine that. But I don't want you to not know about this, so make sure you know. Okay? Anyways, I hope y'all enjoyed this video. I apologize if it was a huge mess. This stuff is insane. And I probably just said a bunch of random stuff that made no sense. So I really hope that you got something out of this, because I don't know what I got out of it other than pain and suffering. You know what I'm saying? Perfect freaking timing. Look at this. Literally, this is meant for people taking the exam. This was me before teaching, and this is me afterwards. This is literally me. I don't know if you can tell, I'm like more out of it than I was when I started. So, you know, I don't know what else to say. If the person teaching it is becoming this, I don't know what's going to happen to the one taking the exam. Now, listen, guys, you better ace your exam, because if you don't, you're going to be forced to send me a message like this. And you don't want to send me that, because I'm going to screenshot your text message and I'm going to include your name and post it in my next exam review video. So I hope that's motivation for you to do good. By the way, please, somebody please draw a benzene like this. I'll give you like $5 if you draw a benzene like this on your exam, because it's diabolical, but it still kind of counts as a benzene. So definitely do that and send me a picture or something. Not during your exam, but like afterwards or something like that. Anyways, best of luck on your exam. I'll see y'all next time. Peace out.